I see, I see. Good morning, every audience. My name is Choji Fukuhara, Japan. I am a chairperson of this morning session concerning about the chemical reactors and technology for targeted applications. Now I will chair from Japan, where has passed enthusiasm of the Olympic and Paralympic Games. And in this session, we have 6 papers, which we presented from Russia, Italy, and Korea. And each presentation has 15 minutes for presentation time and 5 times for question and discussion time, and sharing the PowerPoint file of presenters from their personal computers. Okay, let's go on. The first presenter is from Russia. The presenter is Dr. Dmitry Krasnikov. His paper title is Coupling Electrostatic CLASSIFIER with a spark discharge generator for generation of monodisperse catalyst for single-walled carbon nanotube growth. Okay, and Dr. Krasnikov, please go your presentation.
Okay, thank you, Mr. Chairman, for the nice introduction. Do you hear me well? Do you see my screen well?
Okay, okay, go on.
Okay, thank you. Good morning, dear colleagues. It is my big pleasure to have this talk today and to start this morning session. First of all, I would like to thank the organizing committee that, despite all the problems during the last 2 years, managed to make this nice conference and giving the possibility to share our results, which we believe might be interesting for the community. Carbon nanotube growth itself needed due to the multiple applications that possibly can be fulfilled with carbon nanotubes. So during the last 2 decades, carbon nanotubes have been considered to be an interesting material for a number of applications. And as for the composites or the fuel cells, we already have some products on the market. The implementation of carbon nanotubes in electronics is considered to require a much advanced control over the properties of the carbon nanotubes and, for example, carbon nanotube individuality. So, and for composites, for the fuel cells, batteries, for the electrodes, we can obtain carbon nanotubes usually in the fluidized bed reactors, which are capable to produce thousands of tons of carbon nanotubes per year. But for the electronics, we need individual carbon nanotubes. We need highly oriented and highly structured carbon nanotubes. And for this, the best method is considered as floating catalyst, or as we consider it as aerosol CVD, because the catalyst is extremely diluted. And this dilution allows us to avoid inevitable bundling, inevitable agglomeration of carbon nanotubes. And due to the high surface energy of carbon nanotubes, it is almost irreversible process, because it's easier to break carbon nanotube, agglomerate, than disentangle 2 nanotubes from each another. So usually our aerosol CVD method provides not the powder of carbon nanotubes, not the grams, but square meters of the carbon nanotube thin films, which are interesting material as a transparent conductive electrode, as a exchanging electrode for the solar cell. And during this video, you observe how we can easily manipulate these films and transfer them on PET substrate or on glass. And this material provides state-of-the-art results and can give us new devices. But today we would like to discuss mostly our team of the collaboration. We mostly discuss the process of the synthesis, how to tune the reactor itself. So very general scheme of the reactor is presented on this slide. So we have the catalyst precursor, which is in our case as ferrocene. It decomposes in the hot zone of the reactor to form iron nanoparticles. And actually, the process itself is extremely complicated because those formed nanoparticles, they tend to agglomerate, and at the same time they take carbon inside in order to make the nucleation of carbon nanotubes. And after this, we have like growth process, which is also consists of multiple stages. And then, of course, the activation of the catalyst. And everything happens together in one process. And the problem of aerosol CVD is that you cannot, like fixed catalytic particle, you cannot subject it to some in situ method, because the aerosol particles, if they fixed, they behave differently. And of course, we need to work with this. So in general problem, how to solve this, how to control this non-steady process is actually a requirement of additional study. And tomorrow my colleague, Mr. Eldar Khabushev, will be giving the presentation on how we can try to solve this multi-parametrical task on the optimization of the carbon nanotube. So it will be here tomorrow at the morning session as well. So please join it as well. It is extremely interesting presentation. So today I would like to specify on the activation of the carbon nanotube catalyst, because during the activation we not only define the most of the properties of carbon nanotubes, like its diameter or chirality distribution or utilization degree of the catalyst, so the ratio of the particles, of the iron particles in our case, which can produce carbon nanotubes or cannot. So and in general we use so-called CO-based process, which is boudoir reaction, so disproportionation of carbon monoxide into CO2 and carbon in form of carbon nanotube. And what is important, we can also add small amounts of CO2 to control the process, to etch it a bit. And in general, for the activation, we made like for the activation of this ferrocene-like reactor, the main KPI, as it seems from now, is the speed of delivery of this ferrocene vapor to the isothermic zone of the reactor, because the faster we can do this, the better will be the utilization degree. So we observe the increase in the yield, but still under some processes we will be having turbulence, and of course the yield will decrease. But this strategy, so we consider it is in situ route, in situ formation of the iron nanoparticles from this ferrocene vapor. It is extremely complex because all the processes takes at the same place at the same time, and it is hard to control this process. And for this, we proposed so-called ex situ route. So we wish to form iron nanoparticles not in the isothermic zone of the reactor, but in another aerosol reactor, so-called spark discharge reactor. And we form iron nanoparticles and subject those particles that we able to control into the hot zone of the reactor, and making so-called ex situ route. So what is the spark discharge generator? Actually, the scheme is pretty simple. So we have two electrodes, which actually can be almost every material, like any metal electrodes, or even some carbides or oxides. And we use high power source with the capacitor to to make a breakdown between these electrodes and to form nanoparticles. And we can make the pulsations, making those nanoparticles with like hertz or tens of hertz or kilohertz frequency. And the system is known and can be controlled. So how this spark discharge works? So in general, under the high electric field, we have emission of the electrons from one of the electrode, and it causes so-called electron avalanche. So it's like a chain reaction when we produce more and more and more, and then we form a plasma which makes a breakdown. And this plasma leads to partial evaporation of the electrode material. And when we subject this electrode material to the carrier gas and remove it from the hot zone, we can obtain nanoparticles of the electrode material. And this aerosol can be then subjected to the reaction. And of course, we can control it by the residence time inside of the system, by the breakdown voltage, and so on and so forth. So what is good in this system is that it can be easily controlled, and we can easily change the materials. So iron, nickel, tungsten, or some alloys, or some oxides, or some carbides, and this allows us to find the huge variation of the catalytic material. So, but still, the distribution of the particles is log normal. So when we compare those particles, we observe that CO2 acts differently. So for the spark discharge, it just kills the process. So here is the spectra of the patterns of differential mobility analysis of the aerosol particles, which corresponds to effective size of the particles. And when we consider the yield in form of film thickness, we observe that for the spark discharge reactor, the yield is much lower, and the role of CO2 is just instrumental, just kills the process. While for the ferrocene, we can improve the process first and then kill in presumably similar manner. So in this case, spark discharge reactor, spark discharge generator does not give us like an advancement. So it has lower productivity under the same amount of iron we observe, and of course it has it shows like only negative effect with CO2, and this positive effect we attribute this to the possible role of hydrocarbon residuals of ferrocene on the catalyst surface, and we can discuss it more if there will be a certain question. But what is good in this process is that we can sort the particles. So how to do this? As I already shown on the previous slide, we usually with aerosol particles we cannot fix them, and there is a special method which can be like referred as aerosol mass spectrometry, which called differential mobility analysis, like aerosol spectrometry. The idea is the following: that charged aerosol particles in the electric field will be traveling differently under different electric field and different size. And to fit in the special trap in the system, we can sort the particles and then study them and obtain, of course, these type of distributions for the carbon nanotubes or for example, inactivated particles. So what we did, we coupled this spark discharge generator with the log normal distribution of the particles, which we can control, which we understand, and subjected it to the differential mobility separation to cut the certain size of 0.2 nanometer wide to subject it as a catalyst for the carbon nanotube growth, and then we tried to count what we obtained with this. And for this, we obtained very actually interesting results, that the particles of higher than 5 nanometers do not give us do not give us any carbon nanotubes. So it means that the active particles for carbon nanotubes, which actually cannot be bigger than 4 nanometers, is particles lower than 5 nanometers, which is coincides with general understanding how the CVD process behaves, and that the particles, catalytic particles, is usually of the same size. So, but still, there are the problems with this method. The problems is that the yield is extremely low because we cut only a small fraction of this distribution of the particles. And if we need to subject it to more particles, then it means more carrier gas, and we decrease the amount of the carbon source in the system, and we kill the process anyway. So, and we of course cannot subject carbon source into the spark discharge because, well, in the plasma we'll obtain like everything, all the types of carbon due to atomization of the carbon source. And these are like fundamental limits for this process. So in order to overcome this, we developed a new method which is based on ethylene. And as you can observe, it's more than 99% of nitrogen in the system. So we can concentrate our system mostly into the synthesis itself. And in this process, we observe that the ethylene varies carbon nanotube length, not activation degree. And of course, we can discuss it more if will be a certain question. And of course, we can control this process with hydrogen and to tune it to make to suppress the pyrolysis of carbon of ethylene under the high temperatures that we use. So to wrap up, what we obtained is that in situ activation, the in situ route which we used, which is a ferrocene-based route, it provides the better results still, and the high utilization degree, high productivity of the system. But the use of ex situ route or the spark discharge, when we couple it with DMA, it provides a unique opportunity, which I believe could be interesting for everyone. Unique opportunity to sort the catalytic particles and to obtain the particles of defined size. And for this, we're still in the process because we face the problem of the low productivity, and we made for this new process of the carbon nanotube growth actually. So with this, I would like to thank you for the kind attention and looking for the interesting questions. Thank you.
Thank you very much, Dr. Krasnikov, for the nice presentation and interesting research result work. Okay, now the time for accepting your question and discussion time. So if you want to ask, please turn on your microphone button. Okay, please, anybody? Okay, I have one question. Dr. Krasnikov, in this time you used the spark discharge power for producing the carbon nanotubes instead of the thermal energy. Is it right?
With spark discharge generator, we produce not the nanotubes, we produce catalyst.
Yes.
But
my question is concerning about the catalyst species. In your experiment, you used the iron species.
Yeah, it's a pure iron.
Yes. How about the change of such iron species on your formation of carbon nanotubes?
In general, if I understand the question correctly, in general, we can use almost any alloy here. So actually, not only iron, it could be nickel, iron, titanium, iron, tungsten. So we actually tried a lot of, but this is not the subject of this presentation. But yeah, in general, we obtain the particles with this predefined predefined composition. And
yes, yes.
of course, in the hot zone of the reactor, these nanoparticles, even they can like agglomerate in like grape-like structure. Then in the hot zone, they restructure in this perfect spherical shape. Yeah,
okay, okay. Thank you. Any other question or comment? Please turn on your microphone. It's okay. No? Okay, one more questions. In the V.Ya reaction, for producing the carbon nanotubes, such reaction is favorable for at the lower temperature side, such as the 500 degrees C or 600 degrees C. But how about the heating temperature of discharge phenomena?
Yeah, actually, this is a good question. And of course, yeah, the equilibrium under higher temperatures is shifted to the carbon monoxide. What is important here that our conversion is like 10 to the power -1%. So we can actually collect this gas once again into the loop. So the main idea is to make carbon nanotubes individual. So this is the main KPI. And for this, we usually use 99% of carbon monoxide and only like 0.5% of carbon dioxide. And this is still into the equilibrium is shifted to the formation of carbon.
Thank you very much. It's just time for your presentation. Thanks again for Dr. Krasnikov. Thank you very much for your nice presentation.
Thank you, sir.
Okay, we would like to move the next and invite the next speakers. The second paper is presented by the Italy speaker. Excuse me. The presenter is Professor Giuseppe Pipitone. His paper title is Coupling of Hydrothermal Liquefaction and Aqueous Phase Reformings for Lignin-Rich Steam Valorization. Okay, Professor Pipitone, please. Okay.
Yes.
We can
Good morning.
Yes.
Okay.
Okay.
Can you hear me well? And you see
yes,
the presentation?
Very well, very well.
Okay, thank you very much. Thank you very much, Mr. Chairman, for your introduction, and good morning and good evening to you all. Today I will present you our work on the coupling of the hydrothermal liquefaction and aqueous phase reforming into innovative technologies for the valorization of a lignin-rich byproduct. During the presentation, well, I take the pointer, that is easier. I will show you at the beginning some characteristics of these two processes when they are in a standalone configuration and why it can be meaningful try to couple them in order to increase the total conversion and create some synergy that can eliminate the drawbacks that they have when they are alone. We will go then to the experimental procedures very briefly and then into the results, looking in particular to three aspects that we evaluated in this work that are the use of additives and in the hydrothermal liquefaction reactor and how they impact both the HTL and the APR, the influence of a liquid-liquid extraction before the APR to remove some undesired components, and then we will check at least under with a preliminary mass balance if this process integration is feasible. Then we will wrap up some conclusions and the perspectives. So starting from the HTL process, well, the hydrothermal liquefaction is a thermochemical process that allows us to convert a wet biomass, so without the need of drying our substrate, to convert it into the desired product that is a biocrude. There is an organic phase, which is a calorific value and that can be used as a fuel. So with these reaction conditions depicted here, we follow three schematic steps that are the depolymerization of the biomass, its further decomposition and the repolymerization to obtain as a desired product, as I said, the biocrude. But the main point here is that the biocrude as a problem is oxygenated, still contains too much oxygen, so it needs to be upgraded to be used in a conventional engine. But it's not just this, because if we think that we start with 100 moles of carbon, just a fraction of it is present in the final biocrude, while we lose, in a certain sense, the carbon that is present in the feedstock in a gas phase, reaching carbon dioxide, in the aqueous phase, that is contains most of the carbon that is lost, that is not present in the biocrude, and is also lost in a really diluted stream, so it's difficult to valorize, and then also in the solid phase. So we need to try to overcome these issues that are present and are reported briefly here. In our research group, during the last years, we have looked at the aqueous phase reforming process. That is a catalytic process that allows to convert oxygenated compounds that are present in several aqueous phase side products that are present in the biorefinery streams, to convert them using usually a platinum-based catalyst into a gas stream that is constituted by hydrogen and carbon dioxide. So if we try to follow a simplified reaction stoichiometry, what we can observe is that the oxygenated compound in the first step produces CO and hydrogen, and then the CO in situ, so in the catalyst itself, in the same reactor, is converted through the water gas shift reaction into CO2 and hydrogen. And these are the desired reactions that we want, that allow to increase the carbon efficiency, because the carbon that is lost virtually in the aqueous phase is then recovered here in the gas phase. But we can have also other reactions that I classified here, that is the loss of the carbon pool under producing alkane, which is, it's not really actually a loss because it has a calorific value, but the point here is that we are losing the hydrogen that is here, and it's not as a molecular hydrogen anymore. So this reaction can be evaluated using a couple of indicators that will be used also in the following slides, that just to facilitate your comprehension. There is the carbon to gas, so how much of the carbon that is present in the feed goes into the gas phase. So we are able, thanks to this indicator, to evaluate if we were efficient in removing the carbon from the aqueous phase, and then of course the hydrogen yield. One point in this technology is that even if it can be really effective, we have a low hydrogen production because, as I said before, the aqueous phase is really diluted. So we need to find a suitable application for the hydrogen that is as close as possible to the point of production. So our idea here that we propose is that we integrate the hydrothermal liquefaction and the APR. So at the end of the HTL reactor, we have these 4 phases, but the carbon that is lost in the aqueous phase is not lost anymore because we can valorize it through the APR. We produce the gas phase that is rich in hydrogen. And so we find here in situ, in the same plant, the possibility to utilize this hydrogen for the biocrude upgrade, that is another weak point of the HTL, to obtain the advanced biofuel. In the next slides, I will present you 3 aspects in particular, looking at this process, that are the influence of basic additives in the HTL reactor, the necessity to perform a pretreatment to stabilize the catalyst of the APR, and then at the end a preliminary mass balance on the full chain. So briefly, the experimental procedures, the hydrothermal liquefaction were carried out in a continuous pilot plant unit, and the feed, our substrate, was a lignin-rich substrate that was derived from a bioethanol plant. So it was the waste from a bioethanol plant. And here we focused mainly to 2 phases that are the biocrude, that is, as I said, the desired product, and the aqueous phase that was shipped to the Politecnico di Torino laboratories, where we performed the aqueous phase reforming in a batch reactor. And at the end of the reaction, where we used these reaction conditions, we evaluated the composition of the gas, the liquid phase, and also we characterized the solid phase that is actually the catalyst that we obtained. So going into the detail and the results now, let's see the influence of the additives on the biocrude phase. Well, we can observe, if we look at the biocrude yield that is obtained, we can observe a strong increase of the biocrude yield when we added before the sodium carbonate or in the test with sodium hydroxide up to 27%. And apart from the quantitative information, it is interesting to observe that under a qualitative point of view, these biocrudes are quite similar among them. So there is no difference mostly on the elemental distribution and also on the heating value. I want to highlight here that one strong point of the utilization of sodium hydroxide is also the stability of the reactor itself, because we avoided the appearance of plugging issues because we decreased the molecular weight, the average molecular weight of the biocrude. But this is just one phase of the coin, because we can look, and we should look also at the influence of these additives on the aqueous phase. And you can see here what I mentioned before, very fastly, but this is the plethora of compounds that can be found in the aqueous phase. You can observe that we have carboxylic acids, bicarboxylic acids, hydroxy acids. We have aromatics that are really important, and we will make some observation later on. And we have also alcohol, and I want to point out this issue because, as you see, in particular, methanol was one of the compounds that was influenced by the sodium hydroxide addition. And this is because the literature told us that in this basic conditions, we favor the demethylation of the lignin structure. And so we obtain methanol that is then, thanks to its affinity to its polarity, is in a certain sense is lost in the aqueous phase. Moreover, we identified also several inorganics compounds that are dissolved in the aqueous phase as well. So this is the first point. So we looked at the influence on the hydrothermal liquefaction. We go now into the next step, that is the APR reactor. So you can see here the comparison of the performance of the gas production, hydrogen, methane, and CO2, without the additive and with sodium hydroxide. We see that with the latter, we obtain a higher hydrogen production, even if we had a lower overall carbon to gas conversion. It is worthy to mention here that the carbon balance closure was quite low in this case. And this is because what we know is that the aromatics that are present, as I showed you before, so phenol, catechol, and so on, they have a strong affinity with the activated carbon support. And so they are absorbed by the support, and we lose it both from the liquid phase and from the gas phase. So when we try to close the balance, we don't find the match. But due to this fact, we want to evaluate also some deactivation issues, maybe for the catalyst. And being in a batch reactor, we followed this protocol. So we recovered the catalyst after the aqueous phase reforming. We dried it, and then we reuse the catalyst in the aqueous phase reforming of glycolic acid. That is a really active compound that is present also in the gas phase, but that can be used as a benchmark. Just to make also a reference catalyst, we performed this comparison with a catalyst that was reused after the APR of glycolic acid itself, just to make a fair comparison. So the results are reported here. So if we make the comparison of the test or the catalyst spent with no additive, with sodium hydroxide compared to the reference, we see that we have a decrease both of the hydrogen yield and the carbon to gas. And this was ascribed, as you can see here also on the y-axis on the right, that we had a strong decrease of the surface area of the catalyst. And so, moreover, what I can say is that the sodium hydroxide lost higher surface area compared to the no additive, and this can give us an indication to the for the lower carbon to gas that we obtained here. So we can think that when we used sodium hydroxide, we lost the stability of the catalyst, and so we did not reach the higher conversion compared to the no additive. Anyway, it is really interesting to evaluate and try to evaluate the aqueous phase with sodium hydroxide due to the higher biocrude yield and to the higher oxygen carbon content in the aqueous phase. So we try to understand if we can remove the problem that caused these issues that are actually the aromatic compounds, as I said before, because they kind of plug the pores of the catalyst. So we used a solvent extraction procedure with two solvents, the ethyl ether and butyl acetate, with different solvent over aqueous phase ratio, 1 or 5:1 or 0:1 and 5:1. And what we observed is that, well, first of all, that the organic acid extraction is really low, because we don't want that after the extraction we lose the glycolic acid or methanol, for example. So we see that this extraction was low, so this is a good point. But on the other hand, the amount of aromatics, so this phenol, catechol, and so on, were much higher, and it increased with increase of the amount of solvent that was used. So if we look at the performance of this extraction on the APR, we can briefly observe that there is an increase, a constant increase in the hydrogen production when we used the ethyl ether and when we used the butyl acetate. And when we perform the reuse test, again, we see a deactivation compared to the reference catalyst, as you see here. But anyway, we had a higher surface area compared to the untreated case, so to the case without the solvent washing. So going into the last slide and trying to make a process integration, we try to evaluate as a first step preliminary mass balance. So starting from 1,000 kilograms of carbon per hour in the HTL reactor, the carbon distribution for biocrude and aqueous phase is reported in here. And what we can observe is that if we pretreat the APR reactor with the aqueous phase with butyl acetate, we are able to obtain, assuming this stoichiometry, a simple stoichiometry, we can obtain a significant fraction of the hydrogen that is necessary for the biocrude thanks to the APR reactor. So in conclusion, in this work, we try to integrate these two innovative technologies towards a circular economy approach to reduce significantly the external hydrogen need and to produce a high advanced biofuel. We evaluate the influence of sodium hydroxide that increased biocrude yield and the methanol concentration in the aqueous phase, and observed as the butyl acetate was able to both improve the hydrogen production, remove the phenolic compounds, and maintain the textural properties of the catalyst. In the future, what we want to evaluate is the influence of the inorganics, as I said, that are present also in the aqueous phase, testing alternative pretreatments, for example, using proper solid adsorbents instead of liquid-liquid extraction. And also, we are evaluating at the moment a techno-economic assessment for this integrated plant. And I thank you for your I thank the European Commission for the financial support and you all for your kind attention.
Thank you very much. Nice presentation and interesting result, Professor Pipitone. And now the paper for discuss and question. We have just only short time. We can accept the short question or comment. If you have such a short question and comment, please turn on your bottom Microphone bottom. No? Okay, Professor Pipitone, I have one question. The integration of the two reactor system, in such case, the important point is the mass balance and the treatment speed of each reactor. How about such point?
Do you mean the, sorry, like the, you think about the, let's say, when we think the steady state, we...
steady state, yes,
yeah,
yes.
Yeah, we are we are quite confident that they can be coupled because we are running out now a pilot plant that which in which we are thinking to their really mass balance coupling, and we are confident from the preliminary results that it can be feasible. At the moment, we are working with synthetic mixture that is easier also because it is complex, the treatment of the of the aqueous phase before the APR, and this is the reason why we are working on these alternative technologies compared to the liquid extraction that is really complex and expensive.
I think they're very complex. Yes. Okay. Is there any question or comments? If not, we would like to thanks again, Professor Pipitone. Thank you very much.
Thank you.
And we we would like to invite the next speaker. The next presenter is PhD student Giulia Zoppi from Italy. Her paper title is Aqueous Phase Reforming of Lignin-Rich Liquefaction Fraction Waste for Hydrogen Production. Okay, we are ready for your presentation.
Good morning, can you hear me? Can you see my slides?
Yes, good.
Okay, thank you, Mr. Chairman, for the introduction. I'm Giulia Zoppi, and today my presentation will be about the aqueous phase reforming of the water fraction from the hydrothermal liquefaction of a lignin-rich feedstock. After a brief presentation on how the aqueous phase reforming works, I will present the main results of the work regarding especially tests conducted in continuous mode, before with model compounds, then with synthetic mixture, and at the end we will look into the influence of sulfate. Biorefinery have the goal of producing bioproducts like materials, fuels, chemicals, starting from feedstock that are plant-based or can be also waste. Some of the main processes are pyrolysis, gasification, fermentation, or like hydrothermal liquefaction. This process, however, produces some waste. One of the most important is an aqueous phase that normally is constituted by a mixture of different organic in diluted condition. For example, for the Fischer-Tropsch process, a water containing salt, alcohols, and acid is formed. In this work, we will focus on the water from hydrothermal liquefaction that contains different class of compounds. The solution that is proposed in this presentation is the aqueous phase reforming that has the double goal of abating the organic content and to produce an hydrogen, a gas rich in hydrogen. The aqueous phase reforming is a reforming process who can convert oxygenated hydrocarbon into hydrogen graph. From the GIF graphs, we can see that this reaction is favorable at lower temperature compared with the reforming of alkanes. In these same temperatures, also the water gas shift reaction is favorable and is allowed to have in the same step both the reforming and the water gas shift reaction. Normally, in literature, the most studied compounds are ethylene glycol, glycerol, sorbitol, and methanol. But as you saw also before with Professor Pipitone presentation, the water coming from biorefinery have a more complex composition. The tests that we conducted are conducted in a continuous reactor reactor. Then all the phases that are produced are analyzed, so with micro-GC for the gas composition, the TOC for the total organic content, and the HPLC analysis for the liquid composition analysis. Moreover, we also study the sulfate content thanks to the ionic chromatography. The tests that we conducted are between 250 and 270 degrees with the pressure that is 5 bars above the vapor pressure of the water. So as we said before, in the overview, these are the main covered in this presentation. The first step was to understanding the reaction path of the most important compound present in the water. This is the characterization of an aqueous phase produced from the hydrothermal liquefaction of lignin. The main compounds are glycolic acid, lactic acid, glycerol, acetic acid, and methanol. We also have the aromatics part of the water, but you saw before that these compounds deactivate the catalyst because they reduce the surface area. So when we compose because they need a pretreatment before to not enter in the reactor. Moreover, in this water is also present sulfur as a sulfate, as 40 ppm of sulfate. So now we will start to see the reactivity of these single compounds. We will look especially to glycolic acid, lactic acid, and acetic acid because glycerol and methanol are some of the most studied compounds. They follow the aqueous phase reforming stoichiometry because they have a carbon hydroxylic group ratio of 1:1, so they can follow the reaction. Starting with glycolic acid, that was not studied before in literature, we discovered that this compound is very reactive with very high conversion, almost complete conversion. And in the green dot here, you can see that he also has a high hydrogen production. The hydrogen productivity is defined as millimole of hydrogen per mole of carbon entering the reactor. If we look at this composition, the reaction of glycolic acid produces a gas that is composed mainly of hydrogen and carbon dioxide. And in the liquid phase, we found some small amount of acetic acid that is the product of the hydrogenation of the glycolic acid. However, the amount is really small. Thanks to this composition and to the liquid product, we propose this mechanism. So the glycolic acid, through the carbolization, release carbon dioxide, then hydrogen, and then the carbon monoxide can react with water through water gas shift to increase the hydrogen productivity. The acetic acid is not an hydroxy acid like the glycolic acid, so its reaction is different. It doesn't follow the stoichiometry of the APR. Indeed, he have a low conversion, but almost zero hydrogen production. If we look at the gas composition, it's also clear why. It follows a different path, it's just release carbon dioxide and methane. The lactic acid is an hydroxy acid, but is more complex than the other one. And if we look at his conversion, he has a good conversion of about 60%, but not very high hydrogen production. And his gas composition is very complex. He has also methane and methane and carbon dioxide, and in the water a big amount of propionic acid is present because it's the main product of lactic acid hydrogenation. So in here in the figure we propose this path. So the lactic acid undergo hydrogenation to produce propionic acids that then follow the same path of acetic acid, but it produces ethane and not methane. The lactic acid can also goes to the carbolization to produce ethanol and hydrogen, carbon dioxide, and methane. Now we are looking to the synthetic mixture that we've studied to understand how the molecules behave when they are put together, and especially we will look at the influence of temperature. This test regard to the 270 test. And here you can see the conversion of glycolic acid that is very high, 80% of the lactic acid, the glycerol and the methanol. I didn't insert the acetic acid because when it's put in mixture from previous work, we understood that it does not convert, and moreover, it does not convert to hydrogen, so it's not the main interest in this mixture. When we looked at how the temperature influenced the reaction, we can understand that the decrease of the temperature decreased the conversion of all the compounds. Glycolic acid starts from 80% of conversion at 270, and then arrive to 40% of conversion at 250 degrees. And this is also clear if we look at the hydrogen yield that decrease a lot with the decrease of temperature. And this is true for all the compounds. All the compounds are affected by temperature. The last part of this presentation regards the sulfate influence on the reactivation of catalysts. You saw before from presentation of Professor Pipitone that in organic compounds such as phenols can deactivate the catalyst. But in this water, in the real water, there are also inorganic compounds. And it's known that sulfate can be a problem from platinum catalyst. Here we can look at the results. This is the test without sulfate in the continuous reactor of the same mixture that we saw before. And when we tried with the same mixture but with 40 ppm of sulfate, we can see that the conversion decreased. In the right graph, there is the ionic chromatography results. We can see the starting point of the sulfate, and then we can see that there is an absorption of sulfate during the time of stream. So it's clear that there is a strong decrease on the conversion of all the compounds. In 300 minutes, glycolic acid passed from 90% to 50% of conversion. So the sulfate removal is pivotal to maintain the catalyst performance. Okay, we tried to, with some option, to remove the sulfate, especially with a solid absorption. We tried with active carbon. Here you can see different amount of active carbon and their effect on the mixture. So the absorption of the sulfate is good enough. We arrive to 60% of absorption, but however, there is also a strong absorption on the organic compounds. So this is not a feasible option. Indeed, instead, if we look at ion exchange resins, here is reported the ERA 76. We can see that we have a very high sulfate absorption, 100%, with this ratio of the resin on the water. And we also found an optimum point with comparing the sulfate absorption and organic absorption. The absorption rate is defined as here, so the initial concentration less the final concentration divided for initial concentration. We also look at different kind of resins. So here is reported the worst case, the one with more resin. We can see that both of them absorb completely the sulfate, but they work in different mechanisms. This is just a simplified picture to better understand. The IRA76 as an amine group that is charge plus, and it can bond with the sulfate. Instead, the other resins exchange is a chlorine group with the sulfate present in the water. But this means that there is a release of chlorine in the water. Indeed, if we look at the results, we can see that after that we clean the water with the resins and then we tested it in the same condition, we reach the same performance of the test without sulfate. And the fact that there is no sulfate was confirmed by the ion chromatography analysis. However, the test after the ERA 900 showed a slight the activation, and this is probably due to the presence of chlorine in the water that can interact with the platinum in the same way of the sulfate. To conclude, the main results in this work were that we understood that there is a possibility to valorize the hydrothermal liquefaction water through IPR. Then we understood present in the water showed a great hydrogen yield. Then the temperature has a strong effect. The higher temperature lead to high conversion and high hydrogen production, but also that the sulfate present in the water lead to the activation of the catalyst, so it's fundamental to find a right treatment step. The future work is to apply what we learned with synthetic mixture with the real water and try to test this water in continuous mode, and then also to study the best parameter to run the reactor as co-feeding or whipping gas, or if down up flow. Thank you for the attention.
Thank you very much for your nice presentation, Ms. Julia Zoppi. Okay, we can accept the question and discussion time. So if you want to ask, please turn on your microphone button or raise your hand of reaction button, which located under. Then the moderator will turn on your microphone. Okay, is there any question or comments? No? Okay, so I have one question. In this time, you used the remove the sulfate species. You used the IRA 967 materials, isn't right?
What do you mean? I mean,
resin.
Yes.
IRA 900 resin.
Yes.
How about?
Okay, how about? We saw in literature that they are used to remove sulfate, and from the analysis of ion chromatographies, we see that disappearing of the sulfate group. So there is actually an exchange of this group in the water, and we also see the performance of the reactor that improves.
Yes. But I think there is a limitation of absorbing ability of this resin. How about this? Limitation of absorbing the sulfate species.
Yes, actually, this is also a work in progress. For now, we are studying the better condition. There is also the possibility to use resins that can be activated with hydroxylic group, and they also can be regenerated. So we still have to find the best condition also for the absorption. For now, it was a really easy absorption step, so just a mixture with 90 minutes. And this, yes, it was a batch removal. For now, before we remove the sulfates in batch condition, in cold condition in mixture, and then we tested the water. But of course, to apply this to continuous reactor is different. It can also be a problem with the temperature. So it needs to be studied in different way. For now, we started to understand if it was possible to remove the sulfate and recover and have the same performance of the test without sulfate. But yes, of course, there are limitations. And this is a big part to study. The active carbon maybe are easier, but they take the organic compounds, so this is not an option. There is also the option of make the sulfates precipitate, but then it can be difficult to do it in continuous. So we are studying different options. This was the one that worked better, but of course, it's not at the point that we can really apply yet.
I think you have a many hard time for investigating such items.
Yes, it's difficult, but when you start to work with real water, you cannot pretend that there are not inorganic compounds inside. So
okay,
this is
thank
the
you.
problem. Thank
Thank
you.
you very much. Yes. Is there any question or comments? No? If not, thanks again, Miss Julia Zoppi, for your nice presentation. Thank you very much. Okay, so I would like to the next presenter to invite. Okay, the next presenter is from Russia. Professor Ekaterina Kozlova. Her paper title is Rhodium and Platinum Doped Graphite Carbon Nitride for Photocatalytic Hydrogen Evaluation from Aqueous Solutions of 3-ethanol amine and visible light.
Thank you very much.
Professor Ekaterina, please share your presentation file. Okay, please start presentation mode.
Just a minute.
Yes, we are waiting.
Do you hear me?
Okay, yes, very well. Please
Thank you
go on.
very much for the nice introduction. First of all, I want to thank organizing committee for giving me the opportunity to make this presentation. Today, I want to tell you about the photocatalytic hydrogen evolution from aqueous solution of 3-ethanol, over the photocatalyst based on graphite carbon nitride. The trend towards the reduction in readily available hydrocarbon fuels required the development of new energy sources and new energy strategies. Solar energy use may become one of the most promising way for the development of energy in the future. There are two main directions of solar energy development. It's creation of solar cells or batteries that convert energy of sunlight directly to electricity, and the development of the direct conversion of solar energy into energy of chemical bonds. Photocatalytic water splitting is one of the most promising technique of the solar energy storage and conversion. It was discovered in Japan in 1970s, and the high importance of this topic is confirmed by the exponential growth of the papers devoted to the photocatalytic hydrogen evolution, especially under visible light. This is the mechanism of the photocatalytic water splitting.
is one of the promising methods because this system enables simultaneous wastewater treatment and electricity generation. So I focus on urea oxidation reaction. And water and energy are growing problem in the world. For this reason, I intend to focus on the issue of water energy nexus concept, especially through the direct urea fuel cell, DUFC. In general, fuel cells are well known that can convert the chemical energy of fuel directly into electricity. Specifically, if you use the DUFC, then the simultaneous wastewater treatment and electricity generation. According to DUFC configuration, urea is electrochemically oxidized in an alkaline medium into carbon dioxide and nitrogen. As shown in the following equation, then the generated hydrogen then generated electrons pass through the external circuit, reduce the oxidizing agent. Therefore, DUFC have a high open circuit voltage, OCV, that
recording in progress.
That of hydrogen fuel cell. So in order to enhance the performance of DUFC, its electrochemical reaction must be AQUEOUS. However, this UR contains 6 electron transfer process, which leads to a slow kinetic rate. So UR require the proper electrocatalyst. Many researchers found that nickel is the best electrocatalyst. Also, nickel is abundant material, so it is available. And even compared to noble metal, nickel has better UR performance. In addition, incorporation of additional metallic elements stimulates the nickel-based electrocatalytic activity through the bimetallic synergetic effect. In order to prove the bimetallic synergetic effect, I had designed alloying of nickel-based catalyst with additional metals such as iron and cobalt. In general, the formation of nickel oxide is a key role for urea electrooxidation. However, the onset potential of nickel oxide form from nickel hydroxide was as high, so which further result in a limited cell operation voltage. So as shown in this graph, the introduction of cobalt in nickel-based catalyst electrode shifted the nickel redox peak to more negative potential. After getting this result, I conclude that cobalt is possible reduced overpotential to enhance the operation voltage of DUFC. So in this study, using the nickel phone, nickel and cobalt were deposited by using electrodeposition method. This method is controllable facilitation for the film growth and convenience for the morphology. After electrodeposition, annealing process was carried out because annealing process can enhance the adhesive strength between catalyst film and substrate. And then the optimal ratio for UR can be analyzed with prepared catalyst. In addition, an important factor in determining the performance of a DUFC is the increasing theoretical open circuit voltage OCV by using new oxidant. Applying oxidant rather than oxygen with high reduction potential such as hydrogen peroxide and persulfate are effective methods to increase the cell voltage. Also, from an operation point of view, liquid hydrogen peroxide and persulfate provide more advantages such as easy storage. Therefore, when using the persulfate as an oxidant, then theoretical cell voltage of DUFC is higher than other type of oxidant. In addition, for final goal, continuous production of clean water and power generation, I adopted a forward osmosis membrane as shown in the configuration, because when DUFC is operated, then urea concentration decreases due to the urea electro-oxidized into nitrogen and carbon dioxide. This means that the fuel can be reduced to generate electricity. To make up for this, Espoo membrane will maintain steady urea concentration in analyte. Now I'd like to focus on main result. First, I'm going to look at the anode activity for UR. Nickel and cobalt were electrodeposited according to the molar ratio on nickel foam. As shown in cyclic voltammetry graph, when the increased cobalt contents, it finds to accelerate the formation of nickel oxyhydroxide, which is role of the active intermediate for UR. This means that the lower onset potential of the nickel redox peak. However, when urea in the solution, the increase in cobalt contents result in a general decrease in the current density. This result implies that increase in charge transfer resistance as the cobalt contents increase. So we get the peak current density depending on absence and presence of urea. The ratio of nickel is 9, which is the highest UR activity. In more detail of anodes, compared with the pristine nickel foam, then surface shape was changed in nickel cobalt deposited electrode. The entire surface is developed with permeable shape after the electrode deposition. In addition, surface phase composition was analyzed by Raman spectroscopy. The Raman bands are related to nickel cobalt hydroxide peak. This form can affect the increased UR activity. And in order to use persulfate as an electron acceptor to DUFC, I investigated the PDS reduction performance using the variable carbon-based material catalyst. As shown in CV graph, when PDS is in the solution, the current density increases. In particular, activated carbon electrode exhibit a higher catalytic activity for PDS electron reduction in acidic solution. And the open circuit potential was increased according to the addition of PDS to the solution. This means open circuit voltage of DUFC can be higher. So in here, N-doped activated carbon was used as the cathode to PDS reduction reaction. Until now, the focus was on finding stable anode and cathode for urea electrooxidation and PDS electron reduction. From now on, I focus on effects of analyte, catholyte, and urea concentration on performance of the DUFC. This system exists too many variables. So full factorial design was adopted to find out how variable affects the DUFC performance. I set the 3 independent variables such as analyte pH, catholyte pH, and urea concentration. Considering both the main effects and the interaction effects, then Pareto chart of the standardized effect shows that analyte pH was the most influential variable on DUFC. And in order to check how much power can be generated by the only pH gradient, so pure cell was operated only by the pH gradient without an oxidizing agent and a reducing agent. It was confirmed that there was negligible power generation. In addition, stability test was carried out according to analyte pH. Here, when analyte pH was 14, the system shows higher power value, and analyte pH was 12, the system shows too low power density. Specifically, high analyte pH affects the catholyte pH condition. Activated carbon as a cathode material unstable at high pH with PDS condition. So to high pH has difficulty in real application as well as disadvantage that affects the catholyte pH. Therefore, analyte pH was 13, stable for UFC. And in this study, PDS was used as an electron acceptor, so the performance was compared with the other oxidant. Using the hydrogen peroxide, graph shows the power value is much lower than PDS. Therefore, the use of PDS with a strong oxidizing agent improves DUFC performance. Through experiment on each variable, each condition was determined as follows. So long-term test was conducted using urea and synthetic urine. The power generation is unstable when using only DUFC due to the decrease in urea concentration. To solve this problem, AQUEOUS membrane was adopted. Continuous production of electricity and treated water are possible. And the result of using synthetic urine shows relatively lower power density because the synthetic urine contained various ions and other constituents were present together. Now, I'd like to sum up the main points of my presentation with the following observation. DUFC contain complex parameters, so several things need to be considered to improving the performance. First, I focused on anode and cathode catalysts for urea electrooxidation and PDS electroreduction. And I find out that higher activity of electrode respectively. And then I talk about how variable affects DUFC performance. Analyte pH identified the most important variable effects on the DUFC. So other variables are also considered. Combination of AQUEOUS membrane with DUFC system represents to maintain of the concentration of urea in the analyte for steady electricity production and treated water generation. So that's all I have prepared for you today. Thank you very much for your attention.
Thank you very much for your nice presentation and very interesting studies, Ms. Joshian Kim. So we have many times, so accept some question and comment. Is there any comments or question? You turn on your microphone button or raise your hand of reaction button, which is located under. Is there any question on or comments? No, so Ms. Joshian Kim, I have one question. Okay.
Okay.
Okay. So in your systems, the nickel and the cobalt bimetallic materials is very important fact on your systems. And you mentioned the suitable composition is 90% of nickel, isn't it right?
Right. Yes.
Right. But the nickel form has more power in your reaction systems, isn't it right?
The
Nickel form.
just using the nickel form.
Yes, yes.
Then
not good.
Yes, not good.
Not good.
Performance like pink.
Yeah,
right?
yeah. I see. I misunderstand. So my question is concerning about the composition ratio of nickel and cobalt elements. How effect was done? How to explain such effect of nickel and cobalt components on your electric performance?
That's great.
This
question.
data shows 9% of nickel element is most better.
Yes.
But the 80% nickel elements are a little bit decreased. Why such phenomena was occurred? Just only the difference, 10% elements difference.
Cobalt can reduce the nickel redox potential. So when you only use the cobalt, then urea electro oxidation performance should be decreased in
degrees. Yes, yes.
Yeah. So optimal ratio is important to enhancing the urea electro oxidation. So I find out the optimal ratio. Then
optimal ratio
is nickel is 9. That is the best activity for urea oxidation.
How about the morphology change between the 9 and 8 nickel elements? Morphology change.
Yes.
Do you measure such the morphology change by SEM observation? No?
Yeah, I just check the pristine nickel form and just nickel is 9. I'm sorry, I have I will be analyzed in the future.
Yeah. Okay. Please do your best. Okay, is there any comments or question? No? We have 2 minutes late. 2 minutes. No? So my question again, your system is a little bit decreased in the durability performance test. So what strategy do you have in your future research work?
Oh, sorry, I didn't catch all of that. Could you please?
Your system has a little bit decreased durability performance test. Stability.
Stability.
Stability. Please go. Yes. The later part. Yes. This is time. The 8 hours power is decreased.
Yeah.
What kind of strategy do you have in the newer future research work? No?
I don't have information
Yeah,
about
okay,
this
okay,
yet.
okay. Please think about such the strategy.
Okay, thank
Okay.
you.
Is there any questions? So we just time for finishing. Okay. So let's thank the Miss Jushian Kim for her nice presentation. Thank you very much. And the Professor Katerina Kozlova, come here again.
Yes, I can continue my presentation.
Okay, you have the last 5 minutes for presentation time and the 5 minutes question time. In your presentation from the electron donor parts, maybe. Generally used, the electron donor is
okay, sorry for inconvenience. Thank you very much. The aim of my research was synthesis of active graphite carbon nitrate for photocatalytic hydrogen production. And in this work, we use traditional synthesis technique, the calcination of melamine and dicyanosamide, synthesis with pretreatment of melamine with glucose, and different techniques of platinum co-catalyst deposition from hydrochloric platinum acid and from different nitrate platinum complexes. And I move to results. This is the experiment setup for the photocatalytic hydrogen evolution. We obtained hydrogen in a sealed reaction under irradiation of LED light sources. And we obtained hydrogen from 3-ethanolamine aqueous solution under basic conditions. First, we synthesize our sample by a simple calcination of melamine. And it is the mechanisms of the condensation of melamine. First, we obtained melam, then melon, and then graphitic carbon nitrate. One can see that we obtained a layer structure with platinum. The particle size of platinum was quite high. Then we measured the activity of these samples obtained by calcination of melamine, and it was shown that the activity was not very high, only 450 millimole of hydrogen per hour per gram of the photocatalyst. And then we used a more complicated technique of the graphite carbon nitrate synthesis. It was pre-condensation of melamine with glucose and further calcination. This technique allows one to obtain the samples with interface heterojunctions. The analysis by XPS and NMR confirm the production of graphite carbon nitrate with heptazine and triazine rings. And then we used different techniques for the platinum deposition. It was photo deposition and chemical reduction from hydrochloric platinum acid and the reduction of nitrate complexes of platinum by hydrogen at different temperature. Unfortunately, I haven't enough time, so I move to the results. It was shown that the activity of the photocatalyst prepared with the use of nitrate complex increases with the increase of reduction temperature to 400 degrees and sharply decreases with an increase in temperature to 500 degrees. And the activity of the samples reduced with hydrogen was higher than the activity of samples with platinum deposited by traditional technique. And the highest activity was 5,000 micromole of hydrogen per hour per gram of photocatalyst, and it was possessed by the sample which was treated by hydrogen at 400 degrees. And it should be noted that we achieved 12-fold increase in activity compared to traditional melamine calcination with a decrease in platinum content. This is a comparison of different technique, and one can see that the highest rate of the hydrogen evolution was achieved at the combination of pretreatment of melamine with glucose and further calcination and deposition platinum from nitrate complexes at the temperature of 400 degrees. And also it was shown that the activity of platinized photocatalysts was much higher than the activity of the photocatalyst with rhodium, and the samples with platinum possessed a very good stability during hydrogen evolution. So one can conclude that we proposed effective technique of the photocatalyst synthesis, combine the pretreatment of melamine with glucose and deposition of platinum from nitrate complexes with further reduction by hydrogen. Sorry for inconvenience one more time, and thank you very much for your attention. Also, I want to thank Russian Scientific Foundation for support of my work. Thank you very much one more time.
Thank you very much, Professor Ekaterina Kozlova, for your presentation. We have some accidents, but we can have the question time. And do you have any question or comments? Please turn on your button or raise your hand from the reaction button. No? Okay, so I have one question. So, Professor, in this time you used the polyethanol amine as the electron donor.
Yes, yes, we use striatonol-amine as electron donor.
But the another reference, I watched the another type electron donor such as the methanol or ethanol. How about such the difference electron donor on your performance?
We compared the activity of striatonol-amine with glycerol, with ethanol, and with lactic acid. And the activity with lactic acid was about the same, and the activity with glycerol and ethanol was lower.
Lower.
Yes. And we didn't use methanol because it's poison. We don't work with this substrate.
Methanol is poisoning species.
Yes. So we didn't use it.
I see, I understand. Okay, so any other question or comments? No? Okay, so I think the graphite carbon nitride is very sensitive materials. So the preparation condition very profound effect on the performance. How about that point? Preparation condition.
Yes, we try to do the same synthetic technique for every photocatalyst, and one can see in this slide that the rate of increase of the temperature, the calcination temperature, the time of calcination, all these factors significantly influence the activity of the samples. Yes. For example, this is the dependence of calcination temperature, and one can see that this temperature is the best. Also, calcination time influences the activity, and even as a precursor melamine and this diamide, yes, everything can change the catalytic activity of this material.
Thank you very much. So I understand. Is there any question or comments? No? Okay, so if no, we would like to move to the next presentation. So let's thank again Professor Ekaterina Kozlova. Thank you very much for your presentation.
Thank you very much.
Okay, next, our final presentation from Korea. The speaker is PhD student Haewon Jong Kim. Haewon Jong Kim is here. Okay, so okay, her paper title is the water treatment by a tubular photoelectrocatalytic reactor with electrochemical self-doped titanium nanotube arrays. Okay, please share your presentation file. Okay. Please, the presentation mode start. Okay. We can see your presentation file.
Hello.
Okay, please go ahead. Yes.
Hello, I'm Hyun-Jung Kim from PostTech. In this session, I'm going to present about water treatment by tubular photoelectrocatalytic reactor with electrochemically self-doped TiO2 nanotube arrays. And here's the content. And firstly, I'm gonna talk about the TiO2 nanotube. So TiO2 is the most suitable and candidate for photocatalytic applications due to its biological and chemical inertness. And also, it has a valuable application as a heterogeneous catalyst in photoanode, and it is preferred material because of its low structural integrity over many charge and discharge cycles. However, efficiency of a pure TiO2 is substantially low to utilize it as anode because it's a wide band gap and fast recombination of photo-generated electron and holes. So the key issue is to improve the performance of TiO2 relies on efficient light harvesting, including increase of its photo efficiency and expansion of photo response region, and to ensure efficient number of photo-generated electron and holes reaching to the surface before their recombination. So in order to meet the desired performances, the band structure modification of TiO2 is preferred. So generally, few of the fundamental approaches are implemented for band structure modification via doping with metallic or non-metallic elements or co-doping of metallic and non-metallic elements. So a hydrogen doping in TiO2 lattice is one of the plausible doping methods to form oxygen bacon sheets for application to water treatment. But hydrogen gas is expensive and dangerous, and it requires high temperature. The implementation of the gas in the treatment chamber may be hazardous and not cost-effective. So it has been required that to avoid use of hazardous gas and to implement a simple and low-cost approach to meet the requirements. So Ti3 plus and oxygen bacon sheets cause the defects in the lattice of TiO2, and many researchers have proved that it enhances photo absorption of a material. So most of all, Ti3 plus and oxygen bacon sheet create a trap center rather than recombination center, which result in band gap variation in pristine TiO2. So in this regard, electrochemical self-doping, cathodic polarization can be an effective approach. It is a self-doping of a cathodic polarization. So it can be a strong candidate for making Ti3 plus and oxygen bacon sheets. So in this regard, electrochemical self-doping cathodic polarization can be effective approach. Cathodization of anatase TNT causes oxygen bacon sheets induced by Ti3 plus. So according to the Pourbaix diagram of TiO2, the pH TO2, the pH of electrolyte determines equilibrium potential for Ti3 plus formation. 3 plus formation. So it is need to optimize the cathodization pH and its duration. However, to best of our knowledge, there's no report on the physical-chemical properties depending on the cathodic polarization condition and its optimization. So in this presentation, physical-chemical characteristic of self-doped titanium nanotube, the blue TNT, and its band gap were investigated, and the effect of the pH and duration on the photoelectrocatalytic activity during the cathodic polarization was studied in conjunction with its optimization. So our parametric study was done in step of cathodic polarization, where anatase TNT is set as a cathode to have its proton intercalation. In this step, pH of electrolyte was varied from acidic to basic condition using 0.1 mole of a phosphate copper, and then 170 ampere per square meter of the current was applied with the different duration of from 0 to 180 sec, converting crystalline anatase TNTs into blue-colored nanotube arrays, the blue TNT. And then reduced TNT were analyzed by XPS for oxygen vacancy measurement and DRS for investigating band gap narrowing, and IPCE for estimating incident photon to electron conversion efficiency as a photoelectric catalyst. After optimization of the cathodic process, the best performed blue TNT has been applied as a photoelectrochemical water treatment in forms of a novel cylindrical photoelectrochemical batch reactor. So our samples to demo, so here is the result. Firstly, I'm gonna start with band gap. So our samples demonstrate that its band gap clearly narrowed after cathodic polarization. At the same time, the absorption after self-doping shows enhancement in the range of wavelengths in the visible light region. pH 7 condition shows the smallest band gap and the largest enhancement in the light absorption. To figure out the optimal duration for cathodic polarization, the photocurrent and cathodic current were monitored by switching potential from -1.4 to 1.4 for 4 voltage for 5 sec, respectively. And the result shows that the photocurrent reaches its plateau zone around 200 sec of the cathodization. So IPCE is the parallel to its band gap results. So IPCE is a kind of measurement technique to measure the electron, to measure the photocurrent which is excited by the photon from the light sources. So IPCE result is parallel to its band gap result. pH 7 shows the best photocurrent efficiencies. About the duration of the parameter, the result demonstrate the IPCE increase with the polarization duration, not necessarily. There could be optimal points not only in pH but also in the duration. So here the variation in the chemical state of oxygen and Ti with different pH condition was analyzed by XPS in detail to correlate it with observed variation in band gap of the TNTs. A shoulder of the peak centered at 531.7 electron voltage with higher intensity in blue TNT, which was attributed to TiOH species. The findings from XPS characterization suggest that oxygen vacancy are introduced into lattice of TiO2 during the cathodic polarization. You can see it by comparing pristine TNTs with the other reduced blue TNT samples. And then it means the impurity level induced by Ti3 plus doping exists in the band gap of TiO2 in forms of oxygen vacancies, which can enhance the photocatalytic activity in visible region. So the finding of so here is the TI spectra results of the XPS. As you can see, there is no significant change in Ti2P spectra. The amount of Ti3 plus ions on surface of the reduced TiO2 was too small to be detected by XPS. So electrochemical self-doping is started from bottom of the tube, which is almost below the 1 micrometer, where is out of reach of XPS analysis. I think that's why Ti3 plus was not detected by XPS, on the contrary to the O spectra. In detail, improved property of modified blue TNTs can be mainly ascribed to high concentration oxygen vacancies and surface defects, which causes an increase in observance of a visual light region and introduces new energy band near the Fermi level with a decreased band gap. So following research employed the optimized blue TNTs, the 90 sec cathodized in neutral pH as a photoelectrocatalyst for degradation of polyacrylic acid, which is dispersing agent in cooling water commonly found in industrial wastewater. And it is really problematic compounds when we're using industrial water. So PAA, the polyacrylic acid, is a polymer, and it is challenging to fully oxidize without sufficient amount of OH radicals. As you can see in the results, it is clear that self-doped blue TNTs shows the best performance in PEC, the photoelectrochemical treatment, and it plays a role as a photoelectrocatalyst rather than photocatalyst. And then you can see that UVC is the better option for not only its photoelectrochemical activity, but also further disinfection. So degradation efficiency of so I compared this novel cylindrical photoelectrochemical reactor with the conventional electrochemical batch reactor. So, following research, so the degradation efficiency of two configurations were compared by considering TOC degradation rate constant per unit surface area of a catalyst and incident photon flux into reactors. So, complete degradation of the polyacrylic acid in these two reactors shows the comparable performance, and the scale up of conventional electrochemical batch reactor into cylindrical shape seems successful. So here's the results. For physical chemical properties depending on cathodization condition was investigated, and its optimization condition was unveiled. It is neutral pH condition with 90 sec of the duration. Secondly, clear oxygen vacancies is accompanied by enhancement in visual light absorption and IPCE performance in self-doped blue TNTs. Third, marginal differences in Ti3 plus peak in XPS could be attributed to two-dimensional nanotube structure and its intercalation mechanism. Lastly, the complete degradation of polyacrylic acid in cylindrical reactors shows comparable performance to conventional photoelectrochemical batch reactors. Thank you for listening my presentation. This is my research group and my professor Kang Cho. Thank you for listening.
Thank you very much for your nice presentation and the interesting result work. And so now we have 5 minutes question time and discussion time. Okay, from audience, do you have any comments or question? If you have some question, please turn on your button or raise your hand from the reaction button. No? Is there any comments or question? Okay, so I have one question. In your explanation, I understand the condition of cathodization is very important fact for preparing your materials. So how about the cathodization process will be changed on your materials, such as in this time you used the 170 ampere per square meters, but such the electron charge will affect on your materials. So this is a TNT preparation. So this SEM very regular pore we can see. How about such morphology by changing the cathodization?
There is several reports about the its morphology before the cathodization and after the cathodization, and there is no morphological changes before and after cathodization.
There was no change morphology.
Also in XPS, XRD, the crystalline structure.
Okay, so do you have any question or comments? No? Okay, if not, we are late for the time schedule. So, okay, let's thank Miss Haiwon John Kim. Thank you very much for your nice presentation. Thank you.
Yeah, thank you very much.
Now the all presentation is over. I would like to thank all presenter and audience for the long time attention. And our conference will scheduled in the next schedule is flash presentation times from the 9 o'clock after coffee breaking times. So please connect from the 9 o'clock. Please see you again. Thank you very much for your attention.
Hello, I was a little bit worried since there were no bad.
Here, it's okay.
Sorry. Fine, fine. What time we will start?
We should already start. Okay. Is not able. Okay. Okay, dear colleagues, let us start our poster session. I should inform you that our poster session is already open, though it was actually open maybe a few days ago. But you can go to the conference site, and there you can find the section which is called, I should say it's PDF poster presentations, and then there you will see all presentations, and you should pay attention that you can, clicking on the title of the presentation, you will have access to the poster itself, to the PDF file, and you should pay attention to the letters GG, it's mean Google Groups. You can enter this group regarding any specific poster. And here again, you will have access to see the poster itself, but also you will have the buttons which will make possible to open the discussion. You can use the bottom left button to start the general discussion. So you should understand that if you will write some question or some comment, it will be available to all people who will enter the Google Group space. And medium button is for personal communication with the author. I guess that most authors are present currently in the system, so you can start the personal discussion, or some maybe if you think that your question may be of general interest, you can start some common discussion in this space. So this is some just technical comments. how to work with this. And now I invite Professor Gian-Piero Gruppi to start with the flash presentations of posters.
Andrei, the first contribution will be from Łódź University of Technology. It's on photocatalytic reduction of carbon dioxide in continuous flow photoreactor using titanium oxide-based composites. And it will be presented by Professor Tomasz Maniecki. I guess that who is in charge of uploading the contribution? Is Tomasz Maniecki in the room, first of all? I see him in the participant list. Maybe if you can switch on your video. Professor Maniecki, can you hear us?
I will try to write him. Maybe we can.
I agree. We can switch to the second contribution since I have Dr. Dolganova.
To some later window. Then I will start with another second presentation, which will be made by Irina Dolganova, research scientist from National Research Tomsk Polytechnic University from Tomsk, Russia, on the formation of tetralenes and sulfones depending on the construction of the linear alkyl benzenes film sulfonation reactor. Irina, please. The floor is yours.
Good afternoon, dear colleagues. Today I'm going to tell you about linear alkyl benzene sulfonates and their manufacturing. Linear alkyl benzene sulfonates represent chemicals with a saturated hydrocarbon chain, which contains from 10 to 13 atoms of carbon connected with sulfonate groups. These substances are widespread for production of synthetic detergents. Raw materials for production of such detergents is alkyl benzene sulfonic acid, which is produced as a result of following stages. The first is dehydrogenation of alkanes with obtaining of alkanes of platinum-containing catalyst. The second is a benzene alkylation with alkanes with production of linear alkyl benzene. And the final stage is sulfonation of linear alkyl benzenes in a falling film reactor. On this slide, you can see the generalized reaction network of alkyl benzene sulfonic acid manufacturing with detailed description of sulfonation step. The isoalkanes contained in the dehydrogenation feedstock are converted into light aromatics at dehydrogenation stage. Because of dealkylation and subsequent polymerization, these compounds form tetralenes in the alkylation reactor. And sulfones, which are also byproducts, are formed during sulfonation stage as a byproducts of reactions. In table 1, you can see the main characteristics of sulfonation product and feed flows. The purpose of current work was to show how the sulfonation reactor construction influences the process performance. The research was performed using the computer modeling system of linear sulfonation process. This model isn't steady because it considers deactivation of reaction medium due to viscose components formations. Viscose components here are sulfones and tetralines. To study the influence of the reactor design on the yield of the target product and the dynamics on the highly viscous component formation, we calculated one period between reactor washings using the different parameters of sulfonation reactor. Table 2 shows the values of the contact time, film thickness, and the Reynolds criterion of the liquid film for a reactor with different diameters and number of tubes. Here, the volume of tube space remains constant. With an increase in the diameter of the tubes, the contact surface area decreases, and as a consequence, the volumetric flow rate of the liquid per one tube increases. Due to this, the film thickness and mass transfer coefficient also increase. As a result of calculations performed using a mathematical model, the dependence of alkylbenzene sulfonic acid and highly viscous components concentration on the reactor design was obtained. Here we can see that an increase of diameter of the reactor tubes from 25 to 43 millimeters, the concentration of target product increases during the entire interwashing cycle. However, with further increase in the diameter to 61 millimeter, the concentration of alkylbenzene sulfonic acid decreases. With an increase in the gas velocity and the Reynolds criterion, the mass transfer coefficient increases and formation of unsulfonated residue decreases in favor of formation of the target product. According to this, a decrease in the number of tubes in the reactor to 40 and increase of the diameter up to 43 millimeters while maintaining the reaction volume constant may help us to decrease the concentration of highly viscous components and improve the process performance. That's all. Thank you for attention.
Thank you very much. Irina, we have a time for maybe one question. Okay, Irina, thank you very much. Could you please finish the sharing of the screen? Закрыть настройки просмотра.
Сейчас.
Meanwhile, if the third contribution could prepare, it's Professor Anand Kumar from Qatar University in Doha, and he will present a contribution on modeling of cellulose-assisted combustion synthesis technique for catalyst preparation for hydrogen production from ethanol reforming. The floor is yours. I hope so, at least. Apparently, I'm not so effective in calling people here.
So,
Professor Anand Kumar is in the room.
So Tomasz Manitsky, our first speaker, wrote that he had problems with connections.
Mm-hmm. I don't see. Okay.
Okay.
Okay. So
hello, can you hear me?
Yes.
Yes, yes, and we can restart the program with your contribution.
Okay.
If you share your screen.
It should be now.
We see you very well.
Everything is okay?
Yes.
Yes, we see you, but
we don't see the presentation.
Oh, well, I don't know why. Sorry.
You should switch on the screen, demonstrate on the bottom part of the screen. There is some screen sharing option.
It's turn on, so I don't know why.
Then you should turn, then select the necessary window.
Yes, I know, but it doesn't work. Okay.
Okay, we got it.
Okay.
Very good.
So,
please.
I'd like to show you a part of our result. We work with the reduction of carbon dioxide, photocatalytic reduction of carbon dioxide in a continuous flow reactor using a traditional TO2 based catalyst. For this work, we during photocatalytic reduction of CO2 took place for following reaction: water splitting, CO2 disproportionation, reduction of CO2 to following organic compound. From scientific point of view, the most interesting, the most important are reaction first and 5 and 6. For this work, we construct special equipment. It was made from stainless steel. This reactor is equipped with the heating cooling system. We are able to work in temperature range from 0 to 100 degrees of Celsius. The catalyst is located on the located on the flat P of paper. It's deposited by ultrasonic with use ultrasonic method, and the reactor also is equipped with the quartz glass to quartz glass, which is which can is able to throw ultraviolet light. The ultraviolet light, the lamp were high pressure mercury lamp in our experiment. So we check a few system which contains rather small amount of copper. We didn't see noticeable differences between such a sample. Moreover, the further increase of copper content leads to the decrease of catalytic activity. Moreover, independently from the catalyst composition, we observed a rapidly drop in the activity, and it was connected with the two facts: very fast absorption of reactants on the catalyst surface and relatively slow desorption of the product. It's clearly visible on the IR spectra. The second reason for the deactivate of the surface was the reduction of the surface of the catalyst. If you compare two samples before and after reaction, it's easy noticeable that sample after reaction is significantly darker in comparison to sample before reaction. Moreover, we try to estimate the ratio between ions T2O3 Te and TO2O3 total counts of ions by SIMS technology, SIMS spectrometer, and it's can be deduced that the activation also can be connected with the reduction of the samples. So I have out of time. The main conclusion: the photocatalysis during the production of CO2 undergo the activation during the accumulation. The conclusion are on the slide. Thank you for your attention.
Thank you. And there is time for a short question from the audience. I don't see any hand raising, so I have one. You have it due to the lack of time, but looking at your contribution, it's clear that your strategy of doping the system with lithium or sodium is working.
It's working. It's the activity of such system. If you see in this picture, the activity is significantly higher.
Indeed, and also to some extent also some stability is in solar radiation, in UV irradiation. I wonder, looking at the scale, micromole per gram per hour, is there any technical target, or we are too far from this at the moment?
I think it's at this moment it's interesting only for the scientific point of view. So it's the formation ratio, the quantity of product is too small to technical, to practical use.
Thank you. Thank you for the nice presentation. Next.
Okay, since
Anand Kumar has reached the room, by the way.
I don't see Professor Anand Kumar here. There is no.
We moved to FP4, I guess.
So maybe I'd propose to go to the presentation number 4. Okay.
I agree, Professor Maniek. You should stop sharing the screen, please. Okay, thanks.
Thank you. So the next presentation will be made by Dr. Oleg Manayenkov from Tver Technical University. It's from Tver in Russia. It will be dedicated to magnetically recoverable polymeric catalyst for cellulose hydrogenolysis. Okay.
Okay. Can you hear me?
Yes, we hear you and we see you. It's okay.
Okay. Just a moment.
Very good. As we see the presentation.
Okay. Good morning, dear colleagues. In this work, a novel catalyst based on hypercross-linking polystyrene, HPS, with magnetic properties is proposed for cellulose hydrogenolysis. Biomass-derived polyols such as ethylene glycol and propylene glycol are promising building blocks for value-added chemicals. The scheme 1 depicts pathways for the one-pot transformation of cellulose to ethylene glycol and propylene glycol, and ruthenium-containing catalysts are considered to be the most active catalysts in this process. Hyper-cross-linked polymeric materials are promising carriers, organic carriers for the synthesis of nanoparticles controllers size metals, their stabilization, and subsequent use in catalysis. This slide shows the scheme of catalyst synthesis. The scheme consists of two stages. Stage one is incorporation of magnetic nanoparticles in mesoporous polymeric matrix, and second stage is formation of ruthenium-containing nanoparticles and its reduction under hydrogen atmosphere for 2 hours at a temperature of 300 degrees. This slide shows the porosity data for the initial sample of HPS, magnetic HPS, and the catalyst sample based on magnetic HPS obtained from the nitrogen physisorption measurements. It was shown that with the successive introduction of iron oxide and ruthenium into the pores of sapot, the specific surface area is expected to decrease. The iron oxide nanoparticle size is about 40 plus minus 5 nanometers, and ruthenium containing nanoparticles diameter is about 2 nanometers plus minus 0.5 nanometers. The magnetic properties of the synthesized samples, catalyst samples, were studied. The magnetization curves are presented on this figure. The experimental samples were shown to have a higher saturation magnetization, about 4 electromagnetic units per gram. A high value of saturation magnetization allows for fast magnetic separation catalyst particles from their reaction media. Here you can see this process. The catalyst synthesized have been studied in the cellulose hydrogenolysis. For comparison to other catalysts have been tested as well, commercial ruthenium-containing catalyst based on carbon and ruthenium-containing catalyst based on magnetic silica developed by of us. It was shown that the selectivity of magnetic polymeric catalysts was approximately equal to selectivity of the catalysts based on magnetic silica, which earlier showed a good results in the hydrogenolysis process of cellulose conversion. However, due to the lower percentage of ruthenium, in the new catalysts, its specific activity was higher. To study the catalyst stability, catalyst was separated from the reaction medium using a magnet, and when added with a fresh portion of cellulose, water, and calcium hydroxide, the data presented in table indicates that the catalyst is stable in under hydrothermal conditions of the process. And as a summary, we can draw the following conclusions. Thank you very much for your attention.
Okay, Dr. Monoyenko, thank you very much for interesting presentations and for keeping in time. We have a time for questions, please. I don't see too much hands raised. So I will ask a question. What is your, please comment how maybe large the scale of this approach? So does it work only on some laboratory vessel, or you can apply it, for example, for cubic meters?
Laboratory.
But in general, do you think that it will be possible sometimes to scale up it to some cubic meters?
Maybe sometimes far away.
Okay. Okay, thank you. Then,
thank you very much.
If there is no more questions, then we can go on. Thank you, Dr. Monoyenko.
Yeah, thank you. The next contribution will be presented by Claudia Dimek, a PhD student from Krakow University of Technology. And the title is Metal Organic Framework Supported on Ceramic Foam for Cyclohexene and Benzyl alcohol Oxidation. The floor is yours.
Good afternoon. The topic of my presentation is metal organic frameworks supported of ceramic forms for cyclohexane and benzyl alcohol oxidation. Metal organic frameworks are classified into a new generation of three-dimensional and porous materials. Their structure consists of ions and metal clusters and organic ligands. The combination of these elements allows for obtaining materials with high extremely porosity and specific surface, and the optimization makes that they will be characterized by high thermal and chemical stability. The ever-growing interest of researchers in these materials results the emergence of newer structures with better properties. Due to such rapid development of these materials and their properties, they found application in many fields of science. The aim of the work was to synthesize modern catalysis for selected oxidation reactions to test their catalytic abilities, conversion, selectivity, and their physical-chemical characteristics. And a series of modified H-class-1 materials was synthesized in the form of powders and applied to ceramic forms in order to compare their activity. The obtained catalysts are shown in scheme. In scheme 2 represent the steps for obtaining a structured catalyst. The first step was to prepare the ceramic forms to obtain the best possible deposition of metal organic frameworks of them. The forms were cleaned by sonication in acetone to remove air and impurities. Various variants of H-class-1 were synthesized on forms using the thermal method, and the synthesis condition are shown in table 1. The last stage of the synthesis was the activation of this catalysis. For these results, the materials were washed with ethyl alcohol and deionized water, dry and heated overnight at 110 degrees Celsius under pressure. The test catalysts were into catalytic reaction. In the oxidation of cyclohexane and benzyl alcohol, the catalytic test condition with the use of ceramic forms of powders were the same. Based on the obtained results, reaction schemes were proposed according to which the reaction for both processes take place. Percentage of conversion and selectivity were also calculated, and the results are presented in table 2. The tested catalysts in the form of powders and structured forms show catalytic activity in the proposed reactions with conversion above 60% for the cyclohexane oxidation reaction, except for copper cobalt H-class-1 powder, and a conversion ranging from 10.7 to 62.5 for the benzyl alcohol oxidation reactions. There is an increase in the conversion of the cyclohexane oxidation reaction for copper cobalt H-class-1 and copper palladium H-class-1 materials using a structured catalyst.
instead of a powder. I can invite you to view my poster, and thank you for your attention.
Thank you. Time for a question as usual. Any question from the audience? I don't see hand raising. So I have one short question. You used foams as a substrate instead of pellets or something simpler. Is there any specific engineering reason for doing that? Meaning mass transfer, pressure drop, constraints related to the specific processes, or other possible reason to use foam instead of more simple substrate?
We don't create these foams. Only what we do was create MOFs on these forms, yeah, and test the catalytic.
I understand, but there is one specific reason you selected these commercial foams, or it was just by this support in comparison with other?
Sorry, but I don't understand your question.
No, it's. I was just wondering if using foams as a substrate, commercial, you didn't prepare it, can provide some extra advantage, in your opinion?
We use only this foams and don't prepare other in commercial. Yeah.
Okay. Okay. Thank you, Claudia.
Thank you.
We have a question from Free Captain.
I see.
Yeah. Yeah.
Hi,
Am I in? Okay, Claudia, can you go back to your previous slide with your results? Looking at your, well, nearly one, but last slide, where you show.
In the end.
Sorry, I can hear you.
No, it's somewhere in the end.
Yeah. Okay, number 5. Yeah, here, if you look at the copper and the copper cobalt H-1, you see a clear change in selectivity between the copper one and the copper cobalt one. Moving from selectivity for component B, to component C. Do you have an explanation for that?
No, sorry, I don't think about it. Why it's working this way, yeah.
Okay, good. Thanks.
Thanks.
Okay, let us go on. The next presentation will be made by PhD student Ayur Bunaev from National Research Tomsk Polytechnic University, Tomsk, Russia. It will be about simulation of hydrocarbon pyrolysis non-stationary process. You are welcome, Ayur.
Yeah, okay. One moment, please. All right, can you see it?
Yes, yes, it's okay.
Yeah. All right. Good afternoon or morning, everyone. The relevance of the problem can be considered from 2 really different perspectives. Firstly, simulations and models allow us to achieve significant resource savings, both financial and labor. And secondly, increasing pyrolysis efficiency is relevant because a significant part of polymers is made from monomers obtained with this process. However, coke deposits on the walls of the reactor's coil during process cause some problems like decrease of the cross-section area and local overheats. which can create rather destructive objects, destructions and emergencies. Thus, possible solution is to create non-stationary model, which would give the ability to predict states of the process to reduce the number of emergencies and increase the intergeneration cycle of the pyrolysis reactor. And presented simulation includes 60 various hydrocarbon components with reaction scheme of 148 radical reactions. Changes of concentrations are calculated with 148 exponential equations, which are needed to calculate the rate constants, and as well as 5 for each of the 60 components, which are basically the fourth order Runge-Kutta method. They are needed to calculate changes in the concentration of each component in each of reaction along the length of the pipe, which is expressed in terms of residence time, tau on the screen. And finally, at this stage of model development, adequacy of produced model was tested by comparing calculated coke layer thickness and data from petrochemical plant. However, the data was only about amount of oxygen used for coke burnout and pressure drop just before it, and thus estimation of real coke layer was kind of indirect. Well, that's I guess all. Thank you for your attention, and I'm ready to answer your questions.
Thank you very much for interesting presentations, and I should say you're ahead of time, so you saved 2 minutes. You was too fast. It's okay.
More questions, more fun.
Okay, so we have time for questions. Dear colleagues, please ask. Okay, don't see too much questions. Thank you, Ayur. I suppose your presentations was very clear, and it caused no questions at all. Okay, thank you very much. We'll go
Andrei.
to the next.
Andrei, I have one.
Okay, yes.
As far as I see, of course, in this process, the correct estimation of coke formation rate is a key step. So how critical it is in your model, according to your opinion at least? Is this a well-assessed aspect of the model, or still needs some improvement?
Well, it needs some improvement because we have not evaluated quite adequate energies of activation at pre-exponential factors in these equations, and I still try to find them out. So yeah, it's not the final result. It's somewhere in the middle of the working process.
Okay, you're working on it. Thank you.
Yeah, thank you.
Excuse me, I would have one question. Okay. May I ask one question?
Of course.
On your slide, the exponents, reaction exponents, beta, kj, yeah, you denoted. So what is the order of these exponents? Are they integers or fractional numbers, negative numbers? Can you say something about these exponents? Beta exponents, kj.
Okay. Beta is stoichiometric coefficients of the reactants. I mean, like if we have reaction 2A plus 3B equals C, for example, beta would be those 2 and 3. Yeah.
Okay, no fractions, yeah? You have no fractions.
No, not at all.
Okay, then it's okay. Thank you.
Thank you.
So I guess we can move to the next contribution that will be presented by Dr. Katarzyna Sindera from the Institute of Chemical Engineering of the Polish Academy of Sciences in Gliwice. And the contribution is new streamlined catalytic carriers of enhanced transport properties. Please, the floor is yours.
Okay, thank you very much. Okay, can you see my screen now?
Yeah.
Yes.
Okay. I want to make the full. Okay, can you hear me properly?
Yes.
Okay, but unfortunately I need to make some corrections because I'm a PhD student from the Institute of Chemical Engineering of the Polish Academy of Sciences, but I hope that in the close future that thing that you said will be true, of course.
My best wishes.
Okay, my presentation is to focus on new streamlined catalytic carriers of enhanced transport properties. I will present experimental and CFD results. Okay, it's better. Aim of the research is to study a new generation of structured reactor internals, catalytic carriers, called streamlined or ring structures. They are based on short channel structures. For those who are interested in short channel structures thematics, please see references. The main innovation of the structures is that channel wall cross-sectional shape is modeled like the airfoil profile. The main advantage of that solution is lower pressure loss generated. As we can see, aircraft wing profile type of geometry have drag coefficient value about 1 order of magnitude smaller than in case of TIR and approximately 2 orders of magnitude smaller than in case of other types of geometries like cube, cylinder, sphere, and hemisphere. 3 streamlined structures of regular triangular cross-sectional shape were tested. They were 3, 6, and 12 millimeter long. They were created and analyzed with ANSYS CFD software and 3D printed. The slide contains the picture of demonstrational structure made of polymer, and this is the top back view of the structure. And this aircraft wing profile is easily visible from the top. The slide also contains morphological parameters and dimensions of the tested structures. This slide contains some CFD and experimental details. In case of CFD, 1 single channel of appropriate length was modeled. Boundary regions upstream and downstream of 8 millimeter each were introduced. Polyhedral type of mesh was investigated in case of laminar flow, and velocity range was from 0.1 to 10 meters per second. Experimental heat transfer and flow resistance analysis were performed. Single phase airflow was introduced. Pressure was measured before and behind the structure. And in case of heat transfer tests, structures were heated by strong electric current flowing directly through the metal skeleton. The velocity range different depending on type of the experiment. It was different from flow resistance test and heat transfer ones. The temperature of the structure was measured by 8 thermocouples. 4 were placed in the inlet and 4 in the outlet side of the sample. There are transport flow characteristics of the tested structure, and there are also correlations for monolith and packed bed. In case of pressure drop results, we can see that structure length strongly influence the results. The shorter the structure, the higher the pressure drop. In case of heat transfer characteristic, this influence is not so clearly visible, but I can assure you that it is. The shorter the structure, the better heat transfer properties. The next slides will contain some results of CFD analysis. There are pressure drop distribution in case of 10 meters per second velocity and 0.1 meters per second. And temperature distribution also for case of 10 meters per second velocity and 0.1 meter per second. Conclusions. The novel structures display improved heat mass transfer properties in comparison to monoliths and beneficial pressure drop. The channel length within single structure can be regulated to attain appropriate heat mass transfer coefficients. The experimental results are in good agreement with CFD ones. Maximum relative error does not exceed 26%. And of course, thank you for your time.
Thank you. Very clear talk. It's open for discussion. Anybody from the audience?
Can I ask one question? Katarzyna, it's a very interesting presentation. The question is the following. Usually in any system, there is a rule, some contradiction between pressure drop and mass transfer. So the higher is pressure drop, the more intensive is mass transfer. In your case, you minimize the pressure drop, but what about mass transfer? So if compared to other types of systems, for example, to monolith with straight channels, do you see any loss of efficiency of mass transfer or not?
First of all, we didn't investigate mass transfer. We investigate heat transfer because it's correlated with the Chilton-Colbert analogy, of course. It depends on the channel cross-sectional shape, because in this presentation, I present only triangular structures. We are also investigating the hexagonal and square structure. And in case of hexagonal structures, we can see that this pressure drop to heat transfer ratio is more beneficial.
Okay, thank you.
But the triangular structures are also interesting.
We have time for another question, no more. Okay. Sorry, Piotr, could you?
Okay, thank you very much, Katarzyna, for your presentation. I would like to know something more about your simulations. So you used ANSYS, this is commercial software. How many elements? So this is final volume or final element simulation? I'm not expert in ANSYS.
Okay, we simulated one single channel and all the elements per this one channel with boundary regions was about 1 million.
1 million
elements.
Elements. Total. So you had several million of unknowns, yeah, in the system. You calculated velocity, pressure, and what else? Concentration?
No, there was no chemical reaction, just heat transfer.
Plus heat, okay. And no problems with simulations, convergence, nothing, no issues?
No, because no additional turbulence models were used, just simple laminar.
Turbulence, you used turbulence.
No turbulence, it was a laminar case flow. So
okay.
This is only.
Thank you very much.
Okay,
Katarzyna.
Thank you again. I guess the discussion can continue in the real poster session. So,
okay.
Thanks.
Okay, the next presentation will be made by Professor Valentina Matveyeva from Tver Technical University from Tver, Russia. And it will be dedicated to mono ruthenium and bimetallic ruthenium cobalt polymeric catalyst for livulinic acid hydrogenation. So, Professor Matveyeva, are you here?
Yes, colleagues.
Yes, hello. You are welcome. The floor is yours.
Yes, my name is Linda. I will present instead of Professor Matveyeva.
Sorry.
Not participate today, and I will present this talk.
Okay. You are welcome, Linda.
Hope you see the presentation.
Yes.
hydrogenation of levulinic acid to gamma valerolactone is a part of processing of lignin cellulose biomass, and gamma valerolactone is a platform chemical to produce valeric fuels. Hydrogenation of levulinic acid proceeds via two elementary steps, which one is hydrogenation step and the other is dehydration step. In this work, we studied the activity of several samples based on hypocross-linked polystyrene of Mn100 type, which is the polymer bearing amino groups. And we compared monometallic ruthenium catalyst and bimetallic ruthenium cobalt catalyst. All the catalysts were tested in a batch mode using stainless steel reactor at variation of temperature and hydrogen partial pressure. It should be noted that before the experiment, each catalyst was activated in hydrogen flow. So we also carried out some preliminary study and found that while comparing copper and cobalt, which are often used in hydrogenation of levulinic acid, ruthenium cobalt system represents better results. And while comparing two polymers, a polymer with amino groups is Mn100, and the polymer without any functional groups, functionalized polymers also is a better support than non-functional one. And so we used ruthenium cobalt system based on Mn100 type. And for this kind of system, we write the cobalt content and compare the results with monometallic ruthenium catalyst. And we found that the initial reaction rates go through maximum, which corresponds to the cobalt content 0.1%. For this catalyst, we write temperature and hydrogen partial pressure, and we found that the apparent activation energy is very low, about 17 kilojoule per mole, which likely indicates the internal diffusion limitations. And for other samples with higher cobalt content, which were less active, and for monometallic ruthenium catalyst, the apparent activation energy was about twice higher. So then we tried to find what is the reason that ruthenium cobalt catalyst is more active than monometallic one. We tried to find any mixed compound between ruthenium and cobalt, and unfortunately we found that ruthenium is in the form of ruthenium oxide, while cobalt is likely in the form of hydroxide or chloride, and no mixed compounds were found. And it is noteworthy that the cobalt content was very low, so we cannot find cobalt on the catalyst surface for our optimal catalyst containing 0.1% of cobalt. But the cobalt was present in the catalyst volume, and which was shown by the electron microscopy combined with energy dispersive spectroscopy. And also we noticed that the introduction of cobalt, which was introduced after the ruthenium, results in the change of ruthenium distribution. Ruthenium oxide have tendency to form a rod-like aggregates, while after cobalt deposition, the ruthenium oxide particles distributes more uniformly, which is likely results to the increase of the initial reaction rate, which is our hypothesis. So that's all, and I will come to conclusions. So ruthenium cobalt catalysts are perspective, and the main effect after introduction of cobalt is the change in ruthenium distribution, and ruthenium oxide is a main catalytically active form for hydrogenation of levulinic acid to gamma valerolactone. Thank you for your attention. That's all.
Okay, Linda, thank you very much. Very interesting presentations. So colleagues, we have time for questions. I can ask one while other people are thinking. You said that there is no cobalt, practically no cobalt at the surface of the catalyst, but then what is the function of cobalt in this catalyst? Maybe it's possible to make the same catalyst without any cobalt.
Yes, of course it is possible. Ruthenium oxide is active itself, and after cobalt deposition, we found that the distribution of ruthenium was changed. So even low concentration of cobalt was enough to change the ruthenium oxide distribution. But the mechanism of this effect, I cannot explain. It is known that cobalt compounds can change the distributions of other metals on the supports.
Okay, very interesting.
We deposited it not simultaneously, but sequential. So for me, it is difficult to explain why ruthenium changed its distribution, but the fact is the cobalt influence not as a catalytically active phase.
Okay, okay, Linda, thank you very much.
Thank you for the question.
Colleagues, more questions? Seems not. Okay, Linda, thank you very much again. And we go to the next presentation.
We can move to the next contribution presented by Dr. Yeong Ah from the Korea Institute of Science and Technology of Seoul. And the contribution is design of multi-stage reactor system for the production of high carbon number hydrocarbon fuels from furans by distributing multifunctional catalysts. The floor is yours. We can see your presentation, but we cannot hear your voice.
Sorry. Can you hear me now?
Yes, very good.
Yeah, thank you, Chairperson. Sorry for the long title. So I will talk about design of multi-stage reactor systems for the production of high carbon number hydrocarbon fuels from furans using multifunctional catalysts. So in this work, usually when we try to use lignocellulose for the fuels and chemicals, first we need to decompose lignocellulose, and we can obtain glucose, xylose, lignin, and other compounds. So glucose can be converted into the valuable compounds such as bioalcohols or other compounds. But xylose is very difficult to ferment, and when it is dehydrated during the acidic saccharification, we can obtain popular, and popular can deactivate fermentation. So it is a kind of poison. So because of that, people try to remove popular or valorize popular using this chemical process. And by the hydrogenation, condensation, hydrodeoxygenation, we can obtain this kind of high carbon number isoparaffins, and they can be used as a diesels or aviation fuels. So usually we can try this kind of 3 or 2-step reaction. So furan compounds could be condensed to these C15 compounds, and by the hydrogenation and hydrodeoxygenation, we can obtain these high carbon number isoparaffins.
Apparently everything is freezed here.
Okay.
Andrei, it's a local problem or a general one?
No, it seems to, for example, for me it works okay. So maybe it's a problem on the. Yes, we hear.
Okay.
Sorry, can you hear me now again?
Yes.
Sorry, suddenly the talk was not very good. So anyway, so we can try to obtain these kind of high carbon number hydrocarbon fuels by 3-step or 2-step reaction. But in this study, we try to prepare a thick catalyst bed, and by changing, manipulating local condition of a catalyst bed, and we can attempt a 3-stage reaction and using only one catalyst. So we try to use multifunctional catalyst for condensation, hydrogenation, and hydrodeoxygenation. So the goal of this study is we want to achieve one-part selective production of hydrocarbon fuels. And at the same time, we wanted to understand the effects of multifunctional catalyst on the selective reaction. So these are the results we obtained, and we use ruthenium, nickel, palladium catalyst supported on some acidic support of a tungstate zirconia. And just by adjusting catalyst well temperature, we successfully obtained deoxygenated hydrocarbon fuels. Interestingly, depending on the catalyst we use, we have a different product composition. For example, when we use ruthenium, we have a higher fraction of C15 hydrocarbon, and when we use palladium, we have a lower hydrocarbon, C5 hydrocarbon fuels after this reaction. So selectivity was achieved by different metal catalysts. So in order to understand what happened, we attempted many analysis, characterization. So here, by carbon NMR and proton NMR, we observed reaction networks. And what we found was when we used palladium, hydrogenation was quite preferred. So we obtained just the saturated Pirone compounds, and we obtained the C5 hydrocarbons at the end. But when we use nickel, hydrogenation and condensation occur almost at the same time. So we obtained this kind of C10 dimeric compound, and they could be converted to C10 hydrocarbon. And when you use ruthenium tungstate zirconia, condensation was preferred. So we obtained this kind of C15 trimeric compounds, and finally we obtained the C15 hydrocarbon. So depending on the selection of catalyst, we can manipulate the product composition. So we believe this could be very useful to valorize Pirone compounds to the chemicals and pures. So thank you for your attention.
Thank you. We have time for some questions. Sure. Any from the audience? Well, meanwhile, I have one. As far as understood, you try to combine this multifunctional catalyst in a single multi-stage reactor.
Yes.
With this respect, I wonder about the advantages of using a single reactor multi-stage in terms of heat management, for instance, since the three reactions are all exothermic, I guess, but maybe to a different extent. Could you express your thinking about this?
Yeah. Thank you for the question. Actually, when we before we tried this kind of reaction, usually we use two different reactors, condensation first, and then we tried hydrogenation, hydrodeoxygenation for another reactor. So when we started with this reaction, we thought, initially we thought the hydrodeoxygenation required metal and acid at the same time. Condensation required acid, so we thought we can try all these reactions at one pass, just one pass. So just to reduce the effort for the two different reaction system. Another thing is, as you said, condensation is a kind of endothermic reaction here. Hydrogenation, hydrodeoxygenation is quite significantly exothermic reaction. So there could be certain, heat transfer or some kind of issue could occur here, but we didn't investigate a lot about such issue.
Okay, thanks. Other questions? Apparently not, so we are ready to move to the next speaker.
Thank you.
Thank you.
You're welcome.
The next presentations will be presented from a group of 5 different universities from Russia, USA, and Saudi Arabia. And it will be made by a PhD student, Alexandrina Sulman, from Tver Technical University, Tver, Russia. Alexandrina, please, you are welcome. Alexandrina, do you hear us?
not sure she is in the room.
Yes, I don't see her here. Okay, Jean-Pierre, then it's your turn. Okay.
Well, let's move to the next contribution. Maybe we recover this one. Next contribution is also from Tver State Technical University. It will be presented by Dr. Antonina Stepacheva, and it is on biomass and oil co-hydro processing in supercritical conditions. But
yeah, good day, dear colleagues.
Okay.
I hope you hear me well.
Very well.
Yeah, okay. So just a second. Yeah, okay. Do you see my presentation?
Yes, that's okay.
First of all, I would like to thank the organizing committee for this opportunity to present this report, and my speech will be devoted to biomass and oil co-hydro processing in supercritical conditions. So the global demand in the energy suppliers leads to the intensification of studies for fuels production. And if we see the composition of heavy oil fractions and fuels from biomass, for example, bio-oil, we can see that they have close composition, and it also make it possible to co-process heavy oil fractions and fuels from biomass. Moreover, the main processes that are used for the production of fuels from biomass are similar to those used in refineries. As I said, it is possible to carry out the joint conversion of oils and biomass. The total the group of the processes that are used in this field are called hydrotreatment, but hydrotreatment in typical conditions requires the harsh process, high process temperature, and also consumes high amount of hydrogen. So to solve these problems, it is possible to use the supercritical fluids as a solvents, and this approach allows allows the process to be carried out in the milder conditions, and also the supercritical fluids, supercritical solvents can serve as a hydrogen donors. In this work, we studied the co-processing of model compounds such as anthracene and guaiacol in the solvent mixture consisting from hexane and propanol 2. We used catalysts prepared by the deposition of silica on the polymeric matrix of hypercross-linked polystyrene using subcritical water, and then also in subcritical water the ruthenium and cobalt or nickel were deposited jointly. So the first experiment was to study the influence of solvent mixture, solvent composition, and the catalyst influence on the conversion of separate model compounds. This slide presents the results on the processing of guaiacol, and you can see that an increase in propanol 2 concentration in the solvent mixture increases the conversion of the guaiacol, and also the use of catalysts increases both the conversion of guaiacol and the yield of hydrocarbon products such as monoaromatics, benzene, toluene, and cyclic compounds such as cyclohexane and methyl cyclohexane. So ruthenium nickel catalyst was found to be the most suitable for this reaction, allowing the higher hydrocarbons yield to be obtained. The next stage is the same study for the anthracene conversion, and we can see that also the increase in propanol 2 concentration leads to an increase in anthracene conversion, and also the same ruthenium nickel containing catalyst was found to be the most optimal. So based on the preliminary experiments, we chosen the solvent composition consisting of 40% of propanol 2 and 60% of hexane, and we chosen the ruthenium nickel containing catalysts. Next stage is the study of the influence of glycol content on the conversion of model compounds, and we can see that the addition of glycol to anthracene increases both the conversion up to 100% and the hydrocarbon yield. 6 hydrocarbon yield mean benzene and cyclohexane that was the main product, and the synergetic effect of CC and CO bond breaking can be proposed in this case. So this is the main conclusion of my speech, and I would like to thank my colleagues, and thank you very much for your kind attention. I'm ready to answer your question.
Thank you. And the discussion is open. Questions, comments?
Can I ask a question? Please tell me, so you're talking about the supercritical conditions. And so, for example, when you increase the pressure and temperature, and when you go from usual normal condition to supercriticals, and when you cross the border between normal state and supercritical state, are there any serious, let's say, qualitative changes? So dramatic changes in the chemistry or in reactions, or it's very gradual
yes.
Changes?
Yes, thank you for your question. And yes, of course, when we use the supercritical solvents, we found some changes from the typical reaction mechanism or typical reaction pathways. So in the mainly for anthracene conversion. On this slide, you can see the scheme of the reaction, but as a side product, we found the hydrocarbons, linear and branch hydrocarbons, alkanes or alkanes, with the number of carbon atoms from 10 to 9. The main change in the reaction way for the supercritical fluids.
Okay, thank you.
Okay.
I have a question.
Please, go ahead.
Yes, thank you. My name is Roman Chencha. I work at Sintef. I have actually two questions. The one, I read somewhere that you work at 200 degrees. Is that correct? Or was it higher?
The temperature was 270 degrees.
Okay.
Yeah.
And do you? Okay, that's fine. Do you use also additional hydrogen, or do you use the solvent as your hydrogen donor?
We didn't use the molecular hydrogen. We used the propanol as a hydrogen donor. Yeah.
So how much of the solvent is actually then converted? Because that's also a valuable component. And then often you see that people use quite, I mean, they use certified fuels, nice chemicals as a hydrogen donor in order to upgrade bad biofuels, let's say it like this.
In our experience, we used the high excess of solvent and the concentration was very low, was about 33 grams of anthracene in this per the liter of mixture of the solvent mixture. So in this case, we observed the acetone in the reaction mixture that was obtained from the dehydrogenation of propanol 2, and it was close by the mass balance.
Oops.
Yeah, sorry. For mass balance, it was close to the hydrocarbons obtained and acetone obtained.
Okay, thank you.
Okay, thank you.
Thank you.
So thank you.
Let's go.
We are ready for the next contribution.
Okay, next contribution. I will change the geography because before I was announcing only presentations from 2 Russian cities, Tomsk and Tver. Now we go, fortunately, to Portugal, and the next presentation will be made by a PhD student, Marta Martins, from Instituto Superior Técnico, University of Lisbon, Portugal. Marta, please, welcome. The floor is yours. Marta? Okay, we see you.
Sorry.
It's okay. We have seen your presentation once. Try again. Yes.
You are seeing my presentation?
Not yet.
Apparently, we are at the end of the presentation, so you.
Yes, maybe you should go upstairs. Yeah, to the beginning.
We see the presentation, but it was at the end. Film the presentation.
Okay, I will start again.
Yeah.
So now you are seeing my presentation?
Just a minute. Yes.
Let's wait a bit. You are seeing?
No, again, it disappeared.
No, it looks like when you switch some button, you go to the end of the presentation instead of changing the slide.
Strange thing.
We read in Portuguese some film the presentation, which I guess means end of presentation.
Because I'm in the first slide, so I don't understand.
Try again.
Yes.
You are seeing the first slide?
Yeah, yes, you just have to switch to full screen. Somehow. Yes?
You are seeing?
Yes.
In full screen?
Not
yet. Not yet. Press it again. Yes. Oops.
But again,
no.
You can show it not in full screen. You can show it as is. Okay.
Okay.
We can see it.
Sorry. Okay.
Don't worry.
Okay.
Yes.
So good morning, everyone. I will start my presentation on the topic torrefaction of forest residues using a lab-scale reactor. As you know, forest fires are a big problem in many countries, and observing the distribution of the burned area by type of land in Portugal, we can see that fires consume more area of bush and pasture than forests. So exploit these residues can contribute to forest management, minimizing the risks of forest fires. One of the major difficulties is the collection of the biomass and its transportation to a processing site. In this way, creating torrefaction mobile units can be a solution, converting the raw biomass into charcoal. So we can have energy-dense substance and we can reduce the mass. In terms of experimental parts, we choose a common shrub that is very common in Portuguese forests, and we submit it to a torrefaction process at 250 degrees and 350 degrees during 30 minutes. And then we obtain charcoal, liquid phase, and gas. Because we are interested in charcoal, we analyze after our process using thermogravimetric analysis, in particular using pyrolysis and combustion experiments. As the main results, we can see at higher torrefaction temperature, there is a significantly decrease in the mass of material with an increase in the heat content. We obtain, in terms of lower heating value, 10 megajoule per kilogram using 350 degrees comparatively with raw material that we have around 6 megajoule per kilogram. And we obtain around 90% of energy yield when we use 6 grams, and we can reduce our mass around 50%. Since power densities were very low at 250 degrees, we decided to test higher mass just for 350 degrees. And here what we observed, there is a good impact on the energy yield when we increase the biomass in the reactor. To complement our studies, we also did energy balance on the reactor. We have here several variables, HEL that correspond to thermal losses, UA and HEM of empty reactor, and CP were obtained from the experiments realized with empty reactor. All temperatures were obtained by the data performed with biomass, and the heat supplied to the sample was calculated over the time. Here we have the temperature profile for reactor, set point, and the oven. You can see better the results in my posters and the details there. And what we concluded, torrefaction is a good technique and a promising way to reduce the mass while maintaining the energy content of the shrub. Thank you for your attention.
Okay, Marta, thank you very much for interesting presentations. Okay, colleagues, you're welcome to ask the questions. Maybe I will ask one.
Okay.
So how do you, what is your estimation? How far it is from a large-scale application? So the method you propose.
Now you are thinking scale up the process, and we are thinking how we can feed our process, because we want to be sustainable and create a real scenario. And we analyze the combustion gases from the process, if have enough energy to feed the process. But at the moment, this is not a good idea. So we are thinking on other options to have our mobile systems for this purpose.
Okay, thank you.
Thank you very much, and sorry for the don't show very well the screening.
It's okay. So, any more questions? Okay, thank you very much again, Marta.
Thank you.
Next one presentation.
So we are moving maybe to the last presentation. I'm not sure, since there are a couple of contributions which are pending. However, this is a contribution from Tver State Technical University again, Russia. Will be presented by Professor Yuri Kozitsov, and it's about pyrolysis of coniferous and deciduous wood wastes.
Hello and good morning, college. You see my presentation?
Да, все хорошо.
Yes.
Yes.
The main pyrolysis products process are combustible gas, a liquid fraction, and solid carbon contains residue. The conversion of plant biomass depends the condition of thermal processing. Advantage of pyrolysis at high caloric value of gas as liquid, low containing of tar, the maximum use of potential of processing raw materials, the possibility of using catalysts of various composition to increase the efficiency of the process. So we can do next conclusion that use the pyrolysis in process of processing of plants biomass is a very efficient way to solve these problems. On next slide, you can see the structure of investigation work. First stage, the thermogrammetric study was done. The experimental data obtained by TG analysis were used by kinetic investigation. And the last stage of our investigation was linked with using laboratory setup for slow pyrolysis investigation. And the first stage of the work, a thermogrammetric study of wood waste, samples were carried out using by thermal balance by niche. The analysis was carried out in an argon atmosphere in the temperature range from 35 to 1000 Celsius degree, using a mass spectroscopic attachment, also niche, with a capillary temperature for the selection of volatile thermal destruction process, 300 Celsius degree. According to present data, thermogrammetric curves of samples find a B.Yu sawdust figure A have solid difference in the temperature range from 200 to 400 Celsius degree. It should be noted that the masses of carbon contain residues obtained during the thermal destruction of the initial samples and an inert medium lake, the similar wells. This can be the study of thermokinetics of the process of thermal destruction of food waste samples were carried out in the temperature range from 200 to 600 Celsius degree, various height and range rates of raw materials. Experiment data reflecting the dependence of conversion of the wood waste selected the study of pyrolysis temperature and was studied in a laboratory setup. Moreover, for both types of wood waste under study, the mass fraction of gaseous pyrolysis of products increase, and the mass fraction of carbon-containing residues decreased with increased process temperature. It shall be noted that the dependence of yield of liquid pyrolysis products of the pyrolysis temperature are also different for the samples under study. In the case of birch sandstone, the max fraction of liquid products reach a maximum at the temperature of 35 Celsius degree. And during the pyrolysis of pine sawdust, the amount liquid products increase of the investigation temperature. Conclusion: a thermogravimetric study. Thermogravimetric study of wood waste showed the difference in the course of the process destruction of pine and birch samples, which the most likely due to the different composition and structure of these samples. The heat of combustion gases products pyrolysis of hardwoods of 1-2 times higher than the of conifers, which associated with high concentration of ethane and low concentration of hydrogen, which has a low volumetric heat of combustion. Optimum temperature for pyrolysis is 400 Celsius degree, with fraction size of 1 or 2 millimeters, and other results. Thank you.
Thank you. So time for questions now. Any question or comment? Well, meanwhile, I have one. You mentioned at the beginning of your presentation that your measurements, of course, aim to derive some kinetics for the process. Do you think to some lamp kinetics, or again, these are the starting kinetics or the one that you validated using your TG data?
Kinetic study thermal destructions was carried out of the temperature range from 175 to 600 of various height range of raw materials. 10, 25, and 50 Celsius degree mean to minus in argon using niche thermokinetics 3.1 software. Analysis data presented in this table on slide. You see, can you see this different wood type, beech and pine in this kinetics presented on this table.
Yeah, I see. But according to this table, also the parameters depends on the methods.
Parameter.
Yes, the parameters that are reported in the table, they are different, not only depending on the material, but also depending on the method.
The parameter depends different components of woods. This is hemicellulose, lignin, cellulose. This wood contain different components and different from kinetics parameters. is different components of foods.
Thanks.
Thank you.
Okay, thank you. It seems we have finished. We have completed our flash presentations of the poster session. So thanks to all participants. Gian-Piero, thank you for chairing the session.
Thank you, Andrei. And we recommend to the audience to join the poster section. Maybe, Andrei, we will send some reminder by email to the participants how to join the Google groups.
Okay, maybe I'll say it aloud now, and maybe afterwards, Tatiana, it seems to me, already distributed some instructions, but we still have time to see the posters.
Mr. Chairman, if you don't mind, Alexandrina Sulman will report from my account. She has problems with the connection.
Okay, it was my part of of the program. So again, PhD student Alexandrina Sulman from Tver Technical University, the presentations on design of biocatalyst for efficient one-pot process for cascade reactions. Okay. Alexandrina. Antonina.
She said that she has no access.
Okay.
From my account, it's strange, but I don't know.
Well, I don't know what to do actually.
Yeah.
Okay. So please forward our kindest regards to Alexandrina, but we have to miss her presentation.
Yeah, okay.
So, okay, I invite you to join posters. We still have some time until the plenary lectures, something like 25 minutes to see the posters, to maybe to join some discussions. And as I know, the posters will be available not only today, but it seems to me all during the whole conference. And you have the possibility to visit the poster site a little bit later and see the posters, read, and even discuss. So you can write your comments in Google groups personally to authors and maybe to some wider general discussion. So you are welcome there. You can just have to go to a conference Chemical Reactor 24 site and see the PDF presentation page. And then you will find all posters and two letters. GG means Google groups for each poster, discussion for each posters. So you're welcome there. And I think that our current session is over. Gian-Piero, would you like to add something or not?
Again, I wish to thank all the presenters for keeping on time and the audience for making questions, and again recommend join the poster session if you have other curiosity on these and other contributions which are present there.
So thank you very much, everybody. Goodbye. See you.
Bye.
I think we are right on time, I would say. So I believe that we can start. So good afternoon. My name is Kevin Mahim. I'm professor at Ghent University, and I will be chairing this session. Today, We have this afternoon we have 2 speakers in this session, 2 plenary lectures, and it's a great pleasure that I can announce first colleague that will give a presentation. That is Professor Freek Kaptein, and he will tell us about process intensification through structuring, catalyst, and reactor design. I don't think that Professor Kaptein needs a lot of introduction, but anyhow, I think it's good to look at his resume and be very, very impressed, I would say. So Professor Freek Kaptein is one of the TU Delft's most cited researchers and a winner of the prestigious Hogewerf Gold Medal, prominent figure in the field of catalysis and chemical technology. He graduated from the University of Amsterdam, completed doctorate on heterogeneous catalysis, the metathesis reaction under the guise of Professor Jacob Moulijn, that we also all know. The focus of his research covers a mix of engineering and catalysis achievements, kinetic studies, structure catalysts, and reactors, performance testing, developments, including manganese-based SCR catalysts, de novo synthesis PCDDs, oxidation-resistant nitrogen-doped carbon, and 2 decomposition zeolite catalysts, and so on, including MOF sorption, separation, and membranes. So very, very impressive. So now the EU project on carbon capture using membrane technologies is very relevant in this day and age. Professor Freek Kaptein has authored and quoted over 500 publications and supervises many, many doctoral students. So Freek, it's a great pleasure to give you the floor, and I think we all look forward to your presentation.
Okay, thank you very much, Kevin. Yeah, it's a pity that we can't meet in person in Milano. I would have loved it. But I would nevertheless thank the organizers for introducing me and giving the opportunity to give this lecture. In this presentation, I will indicate how structuring can be used to more efficient catalytic fixed bed reactor operation, saving energy and material. Oh my goodness. Yeah, it works. Okay, so today I will go back a little bit to the basics, recalling some classical reactor operation based on monoliths, and discuss more recent activities illustrated by methane steam reforming and Fischer-Tropsch synthesis, covering the process challenges, catalyst synthesis and performance, and especially the energy management. And finally, we'll indicate what could be the next steps in this field. And I will do that by illustrating structuring on the active phase, on the particle level, and on the reactor level, all for fixed catalyst operations. So what are the issues related to catalytic reactor operation? You can consider the reactor level and the particle level. We can have an ineffective use of the reactor by axial dispersion, more mixing, and radial transport issues, both of mass and heat. Incomplete use of catalyst to diffusion limitations, reducing the effectiveness factor, gas-liquid maldistribution or wetting efficiency, and activity loss by deactivation, fouling, and attrition. And the question is, how can structuring help in with these issues and solving them? Yeah, where is my yeah. Okay, why would you use structured reactors? Well, we have to deal with, if we deal with conventional packing, there's a coupling between phenomena, the particle size, and if you look at the catalyst particle size, you would like to have very small particles because of internal diffusion and solid fluid mass transfer. With respect to the pressure drop in the reactor, you would like to have a very large particle to lower the pressure drop. So there's a link between these two as a classical trade-off in reactor design. If you would take a structured packing or catalyst, for instance, a monolith, you can decouple that link between the two relations. You can choose the thickness of your wash coat or the thickness of the wall of the monolith, so reducing the internal diffusion length scale, and still have a very low pressure drop because of the large hydrodynamic size of the channel. So structure provides an additional degree of design freedom of your reactor. So I will illustrate that for single phase operation. Firstly, go back to the environmental catalysis, the early days of introducing the monoliths or mobile sources for the three-way catalysts, removing NOx, CO, and hydrocarbons. The monoliths have a very low power consumption because there's a very low pressure drop. Moreover, in contrast to having a catalyst bed, there's no attrition by catalyst loss due to the shaking and the vibration motion. If we go to stationary sources, power stations, for instance, we have to deal with dust that will be collected normally in a packed bed. Monoliths have a very low pressure drop. And if we think about selective catalytic reduction, there's an issue of the selectivity. I will focus more on the stationary sources, the selective catalytic reduction of NOx with catalysts based on tungsten or vanadium. This is the chimney where layers of monoliths are being placed with some space in between to allow redistribution of the mixture of NOx and ammonia that is being injected in a stack gas. The two reactions taking place are the NOx reduction in the presence of oxygen and the SO2 oxidation due to the presence of sulfur in the fuel that's being used as a feed. So typical levels of NOx are 1000 ppm, 5% of oxygen, and 500 ppm of SO2. So you want to reduce the NOx in the presence of a far excess of oxygen, and that can be done by the catalyst. Unfortunately, SO2 is being oxidized to SO3 and can form ammonium bisulfate, reacting with the ammonia that's being injected. And if you have a packed bed, you can have bed plugging. But also the monolith can be fouled, as we can see here from the picture. Furthermore, ammonia is fed understoichiometrically to avoid the slip of ammonia, which is even worse than what you try to abate in terms of NOx. Now, the benefits of the monolith are, as already mentioned, dust particles. They can just pass through the monolith channels. And we have the selectivity, which is typical catalyst property, but the oxidation is much slower than the very fast DNOx reaction. Because of the very fast DNOx reaction, the telemodulus for the NOx reduction is pretty large, and the reaction is strongly diffusion controlled. In contrast to the slow SO2 oxidation, where that takes place under kinetic control. So that is proportional to the volume of the catalyst, whereas the selective catalytic reduction is more proportional to the contact area between the gas and the solid. So we would like to maximize that one and minimize the volume of the catalyst. This represents the reduction of the washcoat layer or the thickness of the catalytic wall in that monolith. So a thin monolith wall favors the desired reaction, and structure can steer the selectivity of that operation. Unfortunately, if we have such a small channels, we have a laminar flow profile. And I recall here a presentation of de Gusa for mass transfer limited conversion at the catalysis conference in Roermond in '94, where you can see that parabolic flow compared to plug flow in the reactor leads to lower conversions. They would like to reduce that disadvantage. Fortunately, we have also gas or liquids or reactants entering the channels of a monolith. So we have development of the flow profile, and that is accompanied by development of the mass transfer from the heart of the channel to the wall where the catalyst is located. This is expressed by this relation for the Sherwood number for the mass transfer containing the Grates number. The length of the developing region where you have a higher mass transfer, as a rule of thumb, is given by Birch-Stewart and Lightfoot to be equal to this product of Reynolds and Schmidt. So for a gas operation, the entrance mass transfer region is about 6 millimeter only. So that's very fast developed. But if we look at this relation for the Sherwood number and plot that graphically, you see that at low Grates numbers, we have a much higher Sherwood and mass transfer in a monolith channel. So let's take a typical monolith section of 0.5 meter length, so channels of 1 millimeter. For the gas phase, the Grates number is 5, meaning that we have a far developed mass transfer. But if we go to the liquid phase with a much higher Sherwood number, we operate here at the Grates number of 1,000. So we have much higher Sherwood number. So we are always in a developing mass transfer regime if we operate in liquid operations. And that was the inspiration to develop the monolithic stirrer reactor, where you mount pieces of monoliths on the stirrer bar in a batch reactor, done by Ingrid Hoek and Karen de Lathouder in our group. This is illustrated here by this animation here, where we pour in hydrogen peroxide, which is decomposed over the catalyst coated on the monoliths, manganese oxide. Of course, you don't have to restrict yourself to monoliths. You can also use foams, cross-flow structures, or knitted wire structures. What you can see here is that there's an excellent contact between the monolith channel wall and the liquid, because the oxygen formed leaves the monolithic channel here when we speed up the rotation speed. So there's a good old mixing also of the gas and the liquid in this operation. We also use that for fat hardening, having this very nice white product in contrast to a slurry phase operation here done by Martijn Sievering. And Karen even got the senior molten medal for this type of work. This was a single phase operation, but if we go to multi-phase operation where we have gas and liquid operations, you want to look for the holy grail, where you want to have a low pressure drop and at the same time a high mass and heat transfer, which was already mentioned by Dudukovic. Generally, in co-current gas-liquid flow, we have no so-called Taylor flow. Gas bubbles, trains, and liquid slugs are traveling through the channels. And the mechanism here is that we have in the liquid slugs a circulating flow. So gas or liquid molecules are recirculated and quickly transported from the heart of the channel to the wall. And also the gas molecules can easily reach the catalyst through a very thin layer of liquid at the wall of the channel. So there will be a fast mass transfer of tracer from a slug and also from the gas phase due to this liquid circulation. And the thickness of this layer, which mainly controls the resistance in the film, is determined by the capillary number, viscosity, flow, velocity, and the surface tension. And here we see that the lower velocity gives an even thinner film at the wall, so a faster mass transfer. And we have demonstrated that in the hydrogenation of alpha-methylstyrene, which is limited by external mass transfer. And here is plotted the reaction rate that was observed as a function of the flow velocity in the channels. And we see that the rate goes up at lower flow rates. So even up to 250 times higher mass transfer than in a trickle bed reactor operation. And even 10 times higher than in stirred tank reactors. This is illustrated here also. If we compare monoliths with 400 cells per square inch with operation in stirred tanks or bubbly columns, the energy input that you have to put in these reactors due to break up the gas bubbles and have a good contact between gas and liquid phase, that costs nearly nothing in energy by using the monoliths. So the structure of the monolith keeps the gas bubbles and the liquid slugs intact, and there's no agglomeration. So you exploit the surface tension dominated flow in these small channels. We even thought of, okay, why not using monoliths as a contacting structure? And we looked at the aerobic glucose digestion by biomass. What we noticed after the reaction was that the biofilm that was formed didn't accumulate in the corners, but on the center of the walls of these monolith channels. And the reason is because the gas bubbles that pass through these monolith channels, they leave a thicker accumulation of water, or water in this case, in the corners, whereas there's a very thin film between the gas bubble and the center of the wall. So the transport of the reactant oxygen in the aerobic digestion is much faster at the center of the wall than in the corners. And the biomass dies in the corners and grows at the center of the wall of the monolith channels. And that could also be simulated in this graph. And so due to the best mass transfer, most film growth is taking place on the center of the channel wall. Not only gas liquid is in Taylor flow, but also liquid can be in Taylor flow. We used a liquid-liquid reaction system, the hydrolysis of triglycerides to glycerol, fatty acids, by using lipases, enzymes, which are immobilized on the carbon nanofiber by adsorption. And we had a batch operation with a recycle loop reactor. And here we have the water bubbles in Taylor flow with oil as the continuous phase, which is indicated here. This is the recycle reactor. Here's the monolith section here, indicated here. And the water droplets are passing through the channels in the oil, which you can see here. And they are leaving the monolith here still more or less intact in bubbles. There's no enzyme leaching here, and Taylor flow was easily obtained. the observed activity that we see here in this recirculation reactor was 3 times faster than in an emulsion phase, whereas we can now easily separate the water from the liquid, whereas in an emulsion you have to do special tricks to do that. Also, you could use a membrane-coated reactor, but still the monolith is 15 times faster even. So this also for the regular arrangement or packing in a reactor, we improved the mass transport phenomena very well. So we could decouple the chemistry and the molecular transport process and the hydrodynamics in that operation very well, and individually then optimize the rates of these processes. Yeah, so you can marry scale-dependent and independent processes in a better way by increasing the rates of degrees of design freedom. Now let's go to the energy management. Because that's an important thing in endothermal, exothermal reactions. And I will illustrate that by the methane steam reforming, gas phase operation, and the exothermal Fischer-Tropsch synthesis, where we have to deal with gas and liquids. And the focus will be then on the isothermicity of the operation and to shave off the temperature profile in that reactor. In the early days of the monolith activities, Maria Feliciano, Stephanopoulos emphasized already the need for a monolith geometry, allowing for radial gas mixing that may combine the best heat transfer features of both the honeycomb monolith and the pellet bed geometries. How to improve the radial heat transport? You can do that by convection or by conduction. And that is given in these solutions for the methane steam reforming, where you react steam with methane to produce hydrogen, and also the water gas shift reaction takes place. It's a multi-tubular parallel fixed bed reactor, long tubes hanging from the ceiling of the reactor to allow for expansion if you go to very high temperatures of 800 degrees centigrade. It's a highly endothermal operation. So you need to put in heat, and that's done by methane burning on heating the reactor walls. Catalysts are about 1 centimeter, mini lids, and only the external surface of these mini lids are the active catalyst. Tubes are about 2 inches in diameter. The packing is very critical because there could be present voids where there's no catalyst touching the wall. And then if you have that present in your reactor, then the heat is not consumed by the catalytic reaction. So we have thermal stresses in the reactor wall tube by very hot regions in the tube and lower temperature regions due to the consumption of the heat by the catalyst, and it can lead to destruction of the reactor tubes, leading to disasters. So there are 2 solutions for improved heat transport put forward by the group of Milano and a group related to Johnson Matthey. Use packed conductive foams and monoliths. Yeah. So here's metallic foam, aluminium, copper, Vectrolloy. You fill that with small axial rhodium-based catalyst particles in a random packed bed compared with the coated foam and the packed foam. You can see that in the region where the catalyst is located, the temperature drop due to the endothermal reaction is much lower in a packed foam due to the good heat conduction in the foam. An alternative is by forcing the gas flow through the reactor going from the center to the wall and back here in a radial in and outward flow profile by corrugated sheets with a catalytic coating on that. So these solutions also allow retrofitting of existing reactors. It gives you a more even temperature profile. So on average, a higher temperature level. So the throughput in those reactors is also increased. There will be a lecture tomorrow by Ip Korkendorf with alternative solutions for the reactor heat input. Let's move to the Fischer-Tropsch synthesis, where we can distinguish low temperature Fischer-Tropsch over a cobalt and ruthenium catalyst and high temperature Fischer-Tropsch, mainly over iron catalysts. First one focusing on long chain hydrocarbon formation, the second one on olefins production. This reaction is highly exothermal. The mechanism is a polymeric growth scheme. It's a growth scheme on the surface of the reactor catalyst. Sorry. Chain growth probability is indicated by factor alpha, and the desorption detachment from the catalyst is given then by 1 minus alpha. So this chain growth probability determines what you get in products. If it's high, you get very long products. If it's low, you get only methane back. If the temperature is increased, the chain growth probability goes down. With pressure, it slightly goes up. And if you increase the hydrogen-CO ratio, the feed for the reaction, then the chain growth probability goes down. So that's all important to take into account by the reactor and the product selectivity. So how does heat and mass transfer interfere with this operation? Well, you can apply a mass and heat transport balances to describe the fixed bed operation, the packed bed reactor, and critical here are the heat management and the catalyst effectiveness. So I will go in more detail for that. On the particle level, it's more or less a reaction diffusion modeling where we use the rate expression of Yates and Satterfield, and we multiply that by an activity improvement factor since their publication. So on average, it will be commercial scale a factor of 3. And we have to deal with the chain growth probability alpha and decide for low temperature Fischer-Tropsch, alpha should be larger than 0.9. So we can set up the reaction diffusion equation for steady state. We're using Thiele modulus and the reaction rate with boundary conditions in the center of the particle and at the surface of the catalyst, and solve that. And we do that for both the reactants, the CO and hydrogen. And why is that? Because hydrogen diffuses in the liquid-filled pores of the catalyst much faster than CO. So inside the pores, the ratio of hydrogen and CO changes, increases. So if there are diffusion problems in the catalyst particle, that will lead to a lower C5 plus selectivity. So we try to determine a relation for the chain growth probability based on results that we got with very thin layers of catalysts on the channels of a monolith, 1 centimeter in diameter. So here are the products, wax coated on the monolith and the liquid products. So Ronald de Deugd established a correlation for this alpha based on the hydrogen-CO ratio and on the temperature, and the limiting cases for these relations are according to what you expect. Goes to 1 for very low temperatures and low hydrogen-CO ratios, and goes to 0 for high levels of those parameters. So what do we see now? For instance, here for 0.5 millimeter catalyst particle, hydrogen-CO ratio of 2, you see that indeed CO is consumed and hydrogen reaches the center of the particle. This leads to a reaction rate that increases going inside the catalyst particle due to the alleviation of the CO inhibition of the reaction, but at the same time the alpha goes down to 0. And on average that will give you an alpha of 0.5 to 0.6. So can't we prevent that difference in hydrogen-CO ratio? Yes, we can. And for instance, an example here for 1 millimeter catalyst particle, if we feed hydrogen-CO in the ratio of 0.8 at the surface, you see that the concentrations both of CO and hydrogen are fairly constant. So the hydrogen-CO local synchronous ratio in the catalyst particle remains also fairly constant, and we have a high value of alpha, in this case 0.95. So that is important for the reactor operation. So if we have solved this issue, well, let's go to the heat transport, the heat management in such a reactor. Like we've seen before, we can use structuring by controlling the radial transport. And here we did an experiment with cooling profiles in an cold flow reactor system, in unreactive reactor system for glass speeds. We cooled from 60 to 25 degrees at the wall of that reactor. And we got at different distances of the location in the reactor, these temperature profiles for a glass bead packed bed. If we use these cross-flow structures, open and closed cross-flow structures, so we force the gas-liquid flow zigzag from wall to wall, we had a much more constant temperature profile in radial direction along the length of that reactor. So we have a much better heat removal by using convection to transport heat from in or outside reactor to the wall. Next to that good heat transfer, which is 2 times better than a packed bed, it's a very low pressure drop, and the gas liquid mass transfer is about the same as in a random packed bed for that reactor setup. However, the catalyst holdup in such a reactor, if you coat the catalyst on that structure, is pretty low, only 25% at maximum, compared to the random packed bed of about 65%. But if we fill the channels of the cross-flow structure with small catalyst particles, which is allowed since we have a much higher wall catalyst contact porosity, and we go up to 50% of packing. So increasing the content of the reactor. And we have done an extensive optimization of such a reactor operation, comparing the packed cross-flow structure and the random packed bed, varying all these parameters independently for these 2 operations. The performance indicators are the space-time yield of C5 plus per cubic meter reactor tube or catalyst amount, with some constraints, of course. The result is given here for a random packed bed with an activity of 3 on 10 times the Yates and Setterfield, and for the packed cross-flow structure. And focusing on the space-time yield per cubic meter reactor tube, we can see that in the random packed bed, we have nearly constant productivity due to the strong diffusion limitations in such a packed bed reactor, even if we use much higher activities. The cross-flow structure, which is packed with 3 times Yates and Setterfield activity catalyst particle, has a slightly lower productivity because of the lower catalyst inventory. But if you go to 10 times Yates and Setterfield, you have an enormous gain in productivity. So in that case, the packed cross-flow structure outperforms the random packed bed at high catalyst activities due to the better heat transfer possibilities in that reactor. Can also use larger reactor diameters. This was done for 1 inch, but 2 and 3 inch give about the same heat profiles as a random packed bed. We found that we don't need reactors of 15 meters long. 2 meters is enough to have the normal reactor operation there. These were simulations, but of course, proof in the pudding is in the eating. This is work from the Milano group, where they compared a random packed bed with very small catalyst particle and aluminium foam filled with these catalyst particles in a cooled reactor operation. So what they observed already was that the random packed bed ran away at temperatures at 195 degrees centigrade. And they had already problems in getting the temperature constant, whereas the packed aluminium foam has a very nice constant temperature profile. And if you measure the temperature profiles in the catalyst, in the aluminium foam bed, we only see a very small temperature increase of maximum 4 or 5 degrees. They showed that it has a very stable operation, more than 600 hours, nearly isothermal, and there's an enormous lab scale thermal duty of around nearly 2,500 kilowatts per cubic meter reactor volume. So yes, conductive packed foams can be used for this type of operation. Now, we've been talking about high activities of the catalysts in terms of Yates and Setterfield. Can we make such a more active catalyst? Well, yes, we can. Here I will show you some results of the MOF-mediated synthesis that we used to prepare catalysts for the low and high temperature Fischer-Tropsch reaction. And in fact, you start with a very structured system, for instance, an iron-based MOF, MIL 100, Basolite F300, commercially available, containing 21 weight% of iron. You can impregnate it with a carbon precursor or pyrolyze it directly at inert gas conditions at higher temperatures. Then you get, in this case, an iron carbide in a microporous carbon material. This resulted, depending on the pyrolysis temperature, in these agglomerated iron carbide particles with carbon surrounded. Yeah, depending on the temperature, the iron content increased and also the particle size of the iron carbide increased. Moreover, the iron carbide is of the HEC type carbon, which is quite useful for the high temperature Fischer-Tropsch for olefin production. And here you see for the 500 degrees centigrade, that was the optimal conditions to prepare those catalysts. If we do that and we compare the iron time yields, a measure for the productivity of the hydrocarbons from the syngas, and we compare that with commercial catalysts, we see that our catalyst is at least one order of magnitude more active in terms of a volumetric production. So very high activity. So can't we do that also for low temperature Fischer-Tropsch with the cobalt catalyst? Well, there's a ZIF-67 cobalt-based methyl imidazolate system. If you pyrolyze that, you get this type of system, carbon and cobalt particles. However, cobalt is a very good graphitization catalyst, so it's fully encapsulated by a graphite layer, and it's had a very low activity in Fischer-Tropsch and high methane selectivity. Could be used for nitroarene hydrogenation, however. But after modification, impregnation with a silane precursor, and doing the pyrolysis and removing the carbon, we got 58% cobalt catalyst of a very high, fairly constant activity and an excellent alpha value chain growth probability. Yeah, the particles that we got on cobalt are of the size which are optimal in the low temperature Fischer-Tropsch. So in our case, around 12 nanometer. If we compare now our catalyst with theoretically a pure cobalt catalyst for 210 degrees Celsius, turnover frequency, the crystallite size, etc. Our catalyst activity is about 25% of the maximum theoretically active catalyst. That implies a Yates and Setterfield factor of 50. So indeed, if you want to apply those type of catalysts, you need to have step changes in catalyst and reactor operation. So go for structure, which is nicely illustrated by Robert Gürtel in this graph in Angewandte. So this looks pretty much at our cobalt silica catalyst. So what's now next? Again, citing the wish of Maria Flitzani Stephanopoulos. We need a new geometry allowing for radial gas mixing and having the best heat transfer features to get higher savings in industrial applications. And I think it will be in the packed periodic open cell structures. And we have heard already yesterday the very nice work of Hans-Jörg Freund, the keynote lecture. You can make these type of open cell structure, but you can fill them also with small catalyst particle, increasing the catalyst inventory in such a reactor. I have here an example of work done at Centev by Carlos Grande, where they try to transform the homogeneous NO oxidation in nitric acid plants to a catalytic one catalyzed by platinum. So they produced in cubic isoreticular foams in the reactor, tilted at a certain angle. They anodized this aluminium, made a porous alumina, and added platinum to that. That gave a very highly active catalyst with good heat conduction to the wall. It leads to much smaller reactors, and also it could yield a 10% higher energy recovery. And what I understood is that they are testing now a demonstration test unit of 8 meters long in size, which is still much smaller than the commercial operation in a nitric acid plant. So the next generations of fixed bed catalytic reactors for endo and exothermal processes will be based on structures with heat conducting materials. It could be monoliths, foams, periodic open cell structures, packed with catalyst particles, which are much smaller than the normal ones due to the high contact area of wall, between wall and catalyst particles. And these materials can be produced by 3D printing techniques, both on the particle level, reactor level, and even the reactor and internal structure can be printed in once to have a good contact between the internal structure and the wall of the reactor. And there are several European projects going on there. So, concluding remarks in this sense is that structuring is a tool for process intensification. It allows decoupling of coupled phenomena of kinetics, transport, and hydrodynamics. It gives you more degrees of design freedom. In the process intensification, we have heard several lectures already that you can have high mass and heat transfer at low pressure drops. Can have a good heat conduction in fixed bed, not only for catalysis, but also for other processes where heat generation or consumption is associated with, like adsorption and adsorptive separation. Structures can yield easier scale up or scale down. And additive manufacturing is considered as an enabler of new technologies. Like Carlos Grande said, it's the haute couture in chemical engineering. And you can invent new structures and apply multifunctional systems. And I wouldn't withhold you from an animation where we envisage how a structured multi-phase catalytic reactor would look like and operate, which was done by one of my master students who followed an honors track in chemical engineering and also wished to do something more than only the study. So she also did a second study in design, animations, etc. So here we see the skyline of Rotterdam Europort with a nice fixed bed reactor. Let's have a look inside that reactor. So we enter here at the top, and what we could see, we feed the gas and liquid into this reactor. We see deflectors in the top of the reactor to distribute the smoke, the gas phase. And we also have liquid feeding into the reactor, which is distributed over the large reactor diameter by an overflow system. So the reactor should be really perfectly horizontally. Then due to the overflow mechanism, we see that droplets of the liquid are then trickled on the structure, where we have chosen here for this cross-flow structure. These cross-flow structures are coated with catalysts, and here we see the Taylor flow in these small channels. And these are real animations and visualizations of that such a Taylor flow into cross-flow structure. The walls of these structures are coated with catalyst and contacted with the gas and the liquid. Reactants diffuse into these catalyst particles. They react on metal clusters here in the form of a dehydrogenation forming olefins and hydrogens, and the products diffuse out of your catalyst particle, are taken up by the bulk flow of gas and liquid, and at the end of the reactor, we separate the gas and the liquid, and we collect the products. So that's where I would like to end, and thank you for your attention. And I thank also my former co-workers, PhD students, postdocs in this journey with reactors. And also I wish to memorize my predecessor, Jacob Molijn, and my successors at other universities, at Javier Pérez Ramirez at the ETH and Jorge Gascon at KAUST. And I thank you for your attention. Kevin, floor is yours.
Thank you. I will applaud, and I see a lot of virtual hands at least popping up. I hope we have a few questions from the audience. They can either raise their hand or write something in the chat. I see one question. Yeah, I see Dr. Ouyang. Yeah, please share your question.
Yeah, thank you very much for this very interesting topic. I have actually question regarding the design of this monolithic reactor. I assume you have a lot of geometric parameters to consider. Then and the structure will eventually affect the performance of the reactor. So so considering these geometric parameters, I think basically you have infinite combinations. So could you suggest like an efficient strategy to optimize the structure, the geometry, instead of using a trial and error process?
Yeah, there are a couple of things, depending on what is the limiting process in your operation. If it's a strongly thermal controlled operation, then you should try to maximize at least the heat transport, either by convective transport or by conduction. If you increase the content of the conductive material, of course, you have less catalyst. It depends on the controlling processes, how you should design your reactor and your internal. Yeah. I mentioned also at the end that by this additive manufacturing, you can print both the internal structure and the wall of the reactor. Yeah? What the group in Milano has seen is that the contact between a metallic foam and the wall of the reactor still has the highest resistance against heat transport. So if you can print it in one type, you have already solved that issue again already. And so there are many considerations, many degrees of freedom. There's a lot of things to do. So there's lots of opportunities present in that sense.
Do you see a role for CFD in that context? Or is that a level of complexity that's basically not needed in this phase of design? Or?
Well, I think you can do that. I don't know how much time it costs to set up your CFD model and work out all the opportunities you have. But yes, if convection and mass transport is an issue, you have to improve that part, that aspect of your operation. CFD could save you a lot of experimental work. I don't know. I can't predict what is best. Yeah. I don't know if people have ever been in France in one of the castles near the Loire. There's one castle, Chambord, I think, that has a very peculiar staircase designed by Leonardo da Vinci. I can imagine that that staircase and that construction is a very nice structure for as a reactor internal. So I would challenge one of the scientists present and listening to use that structure in the catalytic reactor.
Okay, well, that's a very nice staircase. So you know what to do. So tomorrow, first job is to simulate the Chambord stairs.
Yeah.
Thank you for the Thank you for the answer.
Okay. Other questions for Professor Captain? Otherwise, I have one more. There's a lot of talk about electrification nowadays. That's you see that things come back in waves in chemical engineering or in science in general. Was a big fuss about electrification several decades ago. How do you see the role in that respect? You spoke about the structured foam reactors. Maybe you could apply power to heat there, or do you see other possibilities? Or will everything be taken over by electrocatalysis, and should we stop with heterogeneous catalysis?
Yeah, but also in electrocatalysis, you need solid catalysts, isn't it?
Yeah.
We have been working on the MOF-mediated synthesis, and we could also make very good electrocatalysts in that way. There are several publications that can be found in the literature. If you think about structured reactors, yeah, also the electrodes could be structured. You can think of how to do that to optimize the contact. If you form from a liquid gas bubbles, you have again something like Taylor flow. You have to remove the gas phase to keep the contact. That are aspects that you can think of. You could conduct the electricity through metallic structure to the electrodes. And tomorrow there will be a lecture by Korkendorf where you can generate heat by electrical current heating catalytic reactors, yeah, providing the heat for endothermal operations. But listen to Ip Korkendorf tomorrow.
Okay, thanks a lot for your very nice talk, and I hope we can give you a big virtual hand just from the audience. So you have a button where you can react and you can clap for Freek. That's at least what I can do, but I will try to give him also a hand that he can at least hear a bit. So thanks a lot, Freek.
Okay.
Very nice talk, and I would say enjoy also the rest of the conference. This brings us to our second speaker of the day, and I saw him already smiling, so he's there. And Fausto, I think, yeah, is smiling again, so that's good. So he's up for it, I assume. So again, also Fausto, this little introduction, but okay, I will do it anyway. So Professor Fausto Gallucci is a professor at the Eindhoven University of Technology. I think he's even now the department chair, which is a heavy job, I would say. So the research of Professor Fausto Gallucci at the Inorganic Membranes and Membrane Reactor Group is related to the development of membranes and novel multi-phase reactors, in particular membrane reactors and dynamically operated reactors. His research focuses on the interaction of heterogeneous catalysis, transport phenomena, and fluid mechanics in these novel multifunctional reactors. Particularly interesting application area are methanol production in zeolite and carbon membranes, methane activation with oxygen selective membranes, Fischer-Tropsch reaction, and hydrogen production by reforming dehydrogenation reactions with hydrogen selective membranes. The membrane reactor research is carried out through integration of in-house developed advanced experiment techniques and experimental proof of concept of novel reactor concept. As a chair of the research group, Professor Fausto Gallucci coordinates and participates in several large European projects, and that's an understatement, I would say. Participates in many, many projects. So, Fausto, I really look forward to your talk, and I would say the floor is yours. Good luck.
Thank you very much for the introduction. Can you hear me? Huh?
We can hear you, yeah.
Okay, so I can start. Indeed, today I will discuss membrane reactors and separation enhanced reactors. And let me see how this works. Yes, so I want to give you first a short introduction on what we do and why we use integrated reactors. And then I will pick one example, which is hydrogen production, and is very related to what the previous speaker said about hydrogen production, and especially reforming reactions. And then I will show you where we are, especially with European projects, how we are scaling up the processes. So first, as in the introduction, I'm from Eindhoven. So our labs are in the south of the Netherlands, but I like to also show our strong collaboration with other groups, and in particular on membranes. We work together with Technalia, and we joined forces 10 years ago. So we tried to share labs and share facilities and even people. So what we do, indeed, process intensification, and process intensification can be achieved in different ways. One is the introduction of reaction separation, and this is probably the biggest theme in my group. We do this with membrane reactors, where the separation is through a membrane, but we do also with other types of separation. Here you see a chemical looping, where we use a solid to make the separation, in particular a metal that is oxidized and basically is removing oxygen from air, and then is reduced, so is releasing the oxygen again. So using a solid, you can also think about a solid that instead of taking oxygen is taking CO2. So in that case, it's not called chemical looping, it's called CO2 looping or calcium looping, depending on the solid that you use. And then another theme is on using or integrating heat management, energy management, and reaction, and we do this with plasma reactors. So today I will show you these two, in particular membrane reactor, sorption reactor, and then a combination of membrane reactor with chemical looping. For the membranes, we start from a really fundamental study, developing new membranes. Here you see, for example, for CO2 hydrogenation, we develop a membrane where part of the membrane in the pores, we have a new liquid, new solvent for the methanol. In this way, you can shift the equilibrium. And then we go to proof of concept and then larger scale reactors. Here you see a bundle of around 125 membranes for hydrogen production. With Technalia, we, as I said, we join forces on membranes, and in Technalia there is more the work on membrane development and also polymeric membranes, and then we integrate inside reactors. So you see that we start from very small to also scale up of the membranes. Today I will show you the scale up of palladium membranes in particular. Now, if we go back to one of our challenges, I think you saw these figures also in previous presentations. One of the challenges is pollution, and especially CO2 emissions. And probably I don't need to convince you that the CO2 emission is related to our activity, but has also a consequence. One of the consequences you can see in this picture, of course, is also a very famous picture. You don't need to be a animal activist to think that this is not good. And especially if you recall, we are in the Netherlands, and if you take models to see what's happening with the water that is produced because of climate change, you will see that part of the Netherlands, a big part of the Netherlands, will be underwater. And unfortunately, most of the population of the Netherlands is close to the sea, so would not be a very good future for our country. So we have to do something, but before doing something, we have to see who is responsible and which solution we can find. So one of the slide, I want to give 3 solutions, according to me, of course. And one solution is reduction of the number of people. So this is not politically correct, but is one of the problems. We have too many people, and of course, each of us should have the same quality of life. So we are not able to sustain the quality of life for all the people. Now, as I said, this is probably something we cannot operate on. What we can operate on is on reduction of the emissions. And you can reduce this by reducing the fossil fuel use. And you can achieve this in 2 ways, using renewables, obviously, but also improving the efficiency of when you use fossil fuel. And for the long run, of course, probably we will have only renewables, but we have still a long way to go. So I think a combination of the 2 is something we have to work on. And the other one is capturing the CO2. So when you use fossil fuel, you produce CO2. It's better to capture instead of emitting that. Now, solution 2 and 3 is something we can work on. If we don't work on these 2 solutions, of course, the Earth will take solution 1 because it's natural. Now, let's go to see who is the responsible for the emissions. And you can find the answer in several reports. I took the report of IPCC. It's an old report. In the new one, there are different numbers, but what is important is the ratio. So if you take the emissions, you will see that almost 1/4 is for agriculture, and then we have transportation and building, and we have industrial use of energy, and then CO2 emissions, and then there is electricity production. So it's more or less divided in 4. Actually, if you zoom in, electricity production is obviously also used by industry, by buildings, and agriculture. Now, of course, you can say, well, industry is producing this, but if you want to be a little bit more fair, I would suggest to use this calculator. And I like to show always this picture, because if you answer to few questions in this website, you will see how much you are responsible for the emissions. And actually, a couple of years ago, I did, because I had to do a presentation like this, I did this calculation, and this is the result. I should say that was before COVID, and I will show you in a second why it's before COVID. So what the website tells me is that according to what I answered, my energy share was finished the 21st of February. And this is already funny because my presentation was the 22nd of February. And also it tells me that if all the people would use the same resources that I used, then basically we would need the resources of more than 7 Earth, which is obviously not sustainable. So the website also tells where I'm using, or I was using most of the energy and producing CO2. And you see that a big share was mobility. But in particular, if you see that it's again divided more or less in 4 to 5, agriculture, mobility, and services are the biggest ones. So if we take mobility, imagine if I could, first of all, reduce the travel, and that's why I said this was before COVID, because Since last year, my mobility share has decreased, as many of you, I think. In any case, if we can improve the efficiency in using the fuel, or even producing different fuels with less impact, then this impact will decrease. Anyway, the take-home message is that we are the responsible, so we have to find the solution. And I want to show also something that was published in Nature, I think 3 or 4 years ago. The paper was called "The 7 Separation That Will Save the World." Now, don't look at the numbers, because in a follow-up publication, this number was corrected, but see the share, also in US, of course, the share of energy use is more or less divided in 4, and a big part is the industrial use of energy. So in this paper, the author also looked at the industrial use of energy, and they found out that up to 55% is due to separations. And of this, 50% is used by thermal separation, distillation, drying, evaporation, and so on. So the authors mentioned that if you could take this thermal separation, and instead of thermal, you would do with pressure, for example, with membranes in particular, you could decrease up to 90% the energy use. And of course, this 90% is very optimistic, but you see what we mean. You can decrease the CO2 emission if you improve the efficiency of your process. And the lecture today is about improving efficiency. Now, what a membrane is, basically is a separation barrier that separates 2 phases. Here I show a membrane for the separation of hydrogen, especially because I will use it today. But the membrane is called membrane if it's selective for the separation. So now, take a membrane. You can use a membrane in a different way. One of the possibilities is the separation indeed. You have a mixture and you separate one product. You can use the membrane as contacting, like was mentioned also in the previous lecture. Why it's nice to use a membrane as a contactor is because if you select the membrane material and the pore size, you can make sure that the contact occurs in the membrane. Generally, if you take an hollow fiber, you can have up to 10,000 square meter per cubic meter of contact area. And then, of course, the contact area means high contact area means also high transport. But as I said, if you select well the membrane, then you can make sure that the contact occurs on the membrane and there is no mixing between the gas and the liquid, if this is a gas and this is a liquid. Then you can use the membrane as immobilization. Think about the catalyst, or in particular, many people are working with enzymes used as catalyst. And the other one is a controlled release of one component. You can think about releasing drug, but you can also think about releasing a reactant to a reactor. Indeed, if you take these 4 functions and you put in combination with the catalyst, then you can have, instead of a membrane reactor. So you can have here a catalyst, so this mixture is reacting, then this is a typical membrane reactor. And the same here, you can put a catalyst on the surface. Here is clear because the immobilization is generally for a catalyst. And here, think about an oxidation reaction. You can feed the oxygen through a membrane in a controlled way. So you can make sure that the selectivity is the one that you want. Now, a membrane reactor is then a combination of a reaction through a membrane and a separation. And this is a typical scheme of a membrane reactor. You have a vessel where there is a catalyst, but in contact with the catalyst, there is a membrane. And now, does a membrane reactor work? As I said, today I will show for hydrogen production. I want to show the work of our colleagues in Italy. They showed that for hydrogen production again, and they took water gas shift as a typical reaction. If you take a water gas shift at industrial scale and you take that as a reference, and that's why they call traditional reactor, this is your reference, and in this particular case, they took the volume of the catalyst, so how big the reactor and how much catalyst you have. If you put a membrane inside and you play with the temperature and pressure, you can decrease the size of the catalyst, so the size of the reactor, up to 30–20% of the original case. So why is the case? Is because a water gas shift is an equilibrium reaction. So if you can remove the hydrogen, you can shift the equilibrium at the same condition to higher conversion. So does a membrane reactor work? Yes. Does a membrane reactor work for all the reactions? The answer is no. So you have a membrane reactor that is a combination of a reaction and a separation. You have to imagine that if you have the reaction and the separation separated in two different vessels, you can optimize the reaction, you can optimize the separation. For example, the reaction can go at a lower temperature and the separation at higher temperature, or the other way around. So you can have the optimum of both. If you put together, they work at the same temperature, pressure, concentration, and so on. So you lose some degree of freedom in controlling the separation and the reaction. Which means that if you want to use a membrane reactor, you should have a challenge either in the separation or in the reaction. And in particular, I suggest that you use a membrane reactor only when you have a challenge in the reaction itself. Which challenge I refer to? If you take an equilibrium reaction, of course, if you fix the temperature and the pressure, you can optimize how much you want the catalyst, but you will reach only the equilibrium conversion. At the same time, if you remove a product, then obviously you can shift the equilibrium towards more product. In this way, you can solve the challenge of the equilibrium conversion by using a membrane reactor. Of course, this separation can be done also with a solid, as I said before, like in sorption, you get exactly the same effect on the equilibrium. And the other challenge you can have is selectivity. Imagine, for example, a series of reaction. Let's say if you have oxidation reaction and you want to do a partial oxidation, either you have low conversion or low selectivity, unless your product you remove during the reaction. In this case, you can increase the selectivity of the reaction. So the first message I want to give is use a membrane reactor or a separation enhanced reactor only if you have an equilibrium or if you have a problem of selectivity. If your reaction goes on without any challenge, don't integrate, because the reactor looks nicer, but at the end of the day, the complete system will be more expensive. Now, as examples, I want to take these two pictures and are about hydrogen production. If you put this picture in words, I like these two sentences. The first one is the hydrogen and stupidity are the most abundant materials in the universe. Our problem is that hydrogen is not concentrated as gas on Earth. And the second one is related to Jules Verne book. I like this because it tells that hydrogen and oxygen will be the fuel of the future for production of heat and lights. Let me say heat and power. Something that I have to say as well is that in the next slide, I don't use references, but most of the work has been produced in the work of Martini, Medrano, which are open access, and also in the work of Rosses. And what is also nice is that Martini is working in Technique now, working on hydrogen, Medrano in a spin-off, working on membrane reactors for hydrogen, and Rosses is working in iGear, which is a company that sells small-scale hydrogen plant. Now, let's go to the hydrogen production. I think you already the inside of a typical reactor for hydrogen production. And if you look at the hydrogen production, most of the hydrogen is produced by natural gas. In some report, you find out that it's 80%. In some cases, they say 70%. In any case, you start from fossil fuel. If you start from natural gas, then you have cleaning of the natural gas. And finally, you go to high temperature to convert the methane, because most of the natural gas is methane, to hydrogen. And normally when you do this reaction, you have to go to extremely high temperature because it's very endothermic, as Frick just showed you. Then you have CO. You have to convert the CO in water gas shift. And after the conversion of CO, then you have hydrogen with CO2, a little bit of CO, a little bit of methane, depending on the pressure and temperature of the different steps. So you have to purify the hydrogen. And of course, you can produce very pure hydrogen. The higher is the purity of the hydrogen, the higher is the off gas that you have with some remaining hydrogen. That's not a big problem in a conventional system, because you take this off gas, you mix with a little bit of methane, and then you burn, because you have to go to high temperature. So at the end of the day, if you make a black box, you have air, you have natural gas, you have water, because you do water gas shift, steam reforming and water gas shift, and you get hydrogen. And the problem is that you have CO2 mixed with nitrogen. So what we want to do is trying to avoid this CO2 mixing. So we would like to have natural gas converted to pure hydrogen and CO2 not mixed with the nitrogen. So in this way, we can have our product starting from natural gas, but without pollution. Now, if I take the reaction, just for this slide, let me simplify it. I take methane and water. I get CO2 and hydrogen, and clearly this is an equilibrium reaction. So there is a challenge of the equilibrium. The maximum I can get is the equilibrium conversion of methane, and this endothermic. So I have to go to high temperature. How can I improve this this reaction? Basically, in two ways. I can remove either CO2. If I remove the CO2, then I have generally absorption enhanced reactors, because this reaction is very high temperature. So the only way you can remove the CO2 is with a solid. You cannot do with a polymeric membrane, for example. And the other way is to remove the hydrogen. Now, the effect on the equilibrium is the same. So if you remove a product, you shift the equilibrium. So in principle, either removing CO2 or hydrogen, I can have complete conversion of methane at lower temperature. The difference is that if you remove CO2, since you do sorption, then you have to do the desorption. So CO2 will be a lower pressure, hydrogen will be at higher pressure. CO2 will be more pure, hydrogen will be less pure. So you need some more separation for the hydrogen. If you separate hydrogen through a membrane, then hydrogen will be a low pressure, because you have to use a delta P for the membrane separation, and will be more pure. CO2 will be at higher pressure, but will be less pure. So if you need pure CO2, you have to do a separation later on. Now, let's start with the first one, which is the sorption enhanced reactor. And in this case, I want to show the real reaction. You have, of course, the gas phase. I go fast because these were shown already. And this is an equilibrium reaction, is highly endothermic. So you can, as I said, you can remove the hydrogen, use a membrane, you can remove the CO2. And if you remove the CO2, you can use, for example, calcium oxide. And the calcium oxide reacts with CO2. Why this reaction is very nice is that if you do calcium oxide and it reacts with CO2, this carbonation reaction is highly exothermic. So if you put together the reaction, you have the total, which is this one, which is basically energy neutral. Now, if this is energy neutral, it's already very nice, because you remove the CO2 and you have the pure hydrogen, or purer hydrogen, I would say. What is the problem is that calcium oxide is a solid, and at a certain point, all the calcium oxide is converted to calcium carbonate. So if you want this reaction to proceed, you have to regenerate the calcium oxide. And of course, if this reaction is very exothermic, if you do the other reaction, the opposite is very endothermic. So you have to supply the energy. Recall that there is no separation that is for free. So if something looks that is extremely nice, then there is a catch, and of course you have to regenerate. Now, how you supply the energy here? Since I want to avoid CO2 into the nitrogen, I cannot regenerate by burning something. So what I can do is I can use copper inside the system and use another reaction, which is copper with oxygen. So if I have copper and I put together with the calcium, copper reacts with hydrogen, CO or methane, and is exothermic. So if I have copper oxide and I react with hydrogen, this reaction is exothermic. So the energy that is released, of course, can be used for regenerating the calcium carbonate. Again, this is a reaction that is very well known. Of course, at a certain point, the copper will be the copper oxide will be all copper, so you have to regenerate. And in this case, you can regenerate with air. So copper plus oxygen will give copper oxide. The nice thing is that if you take this and this together, at the end of the day is basically a conversion of, let's say, for simplicity, let's take methane, is a conversion of methane with oxygen. But the CO2 is released in this reaction, and the nitrogen remains in this reaction. So, which means that the CO2 and the nitrogen are separated to each other. Now, I have a system of reaction and a system of solids. How can I make this reactor working? And this has been proposed, and there is also a patent from our colleague in Spain. Basically, this reactor can work only if you operate in at least 3 steps. So in the first step, you have the steam reforming. The calcium oxide is becoming calcium carbonate, so you remove the CO2 and you produce relatively pure hydrogen. Copper doesn't do anything because copper plus methane doesn't react. In the second step, you have copper that is converted to copper oxide. The calcium carbonate doesn't do anything, so the CO2 is not released if you do this step in a clever way. And then finally, you have the final step in which copper oxide is reduced to copper, release the energy, and then this energy is used to calcine the calcium carbonate. Now, this scheme requires at least 3 steps and requires at least 3 solids: calcium oxide, copper, and of course the catalyst for the reforming reaction. Now, you have sorbents and copper, and it's very important to have a very good heat transfer between the copper and the sorbent, because it's the energy released by the copper that is reactivating the sorbent and releasing the CO2. And of course, here there is a lot you can do. If you take the presentation before, of course, one of the solutions that we also worked on was a structure system in which the structure was coated with copper and sorbent. Of course, you can also have separate pellet, which is the first thing you would do when you do the demonstration, and then you can have mixtures inside the structure, or even better, you can produce composite material where copper and calcium oxide or sorbent in general are very close to each other. Now, as I told you, you need at least 3 steps, A, B, and C. But in reality, when you do the optimization, you need more than 3. And in particular, because when you do the oxidation of copper when you do the oxidation of copper in copper oxide, you cannot use air, but you have to use air with a little bit of oxygen. Otherwise, the energy released there will also make the CO2 released. And if you release the CO2 in this step, then it will go with nitrogen. In any case, you will find a lot of papers also from our group, but especially from the group in Spain, describing this particular combination of reactors. And now, at which temperature and pressure you have to operate the reactor, you have to look at the equilibrium. And the most important equilibrium is the CO2 removal, so the carbonation of the calcium oxide. So if you take the calcium oxide, depending on the partial pressure of CO2 in the gas phase, you can have calcium oxide or calcium carbonate. And this concentration is called the equilibrium concentration and is given by this equation here. So you see that at different temperature, you have different equilibrium conversion or equilibrium concentration of CO2. Now, since you want to capture as much as possible the CO2, it's much better if you work at high pressure, because you see that at high pressure, for a large temperature window, you have that the partial pressure of CO2 is almost 0, which means that you can capture completely the CO2. And then if you want to release the CO2, it's better to work at lower pressure, because then at lower pressure and a relatively low temperature, you can, the equilibrium is increasing, and then you can much easily convert the calcium carbonate to calcium oxide. So by using only the equilibrium, you can see which is the temperature and pressure window of the 3 steps. And then, of course, what is the concentration of the calcium oxide and the copper oxide depends on the productivity of your reactor. So if you take in this particular case, we found out that the best would be 20% of calcium oxide. Now, by using this, you can make optimization of the system. And what we did is indeed using particles. We have a relatively big reactor to be a university. You see it's quite a big reactor. We can put up to 7 kilos of material inside. And basically we did the demonstration. And you see here that we did a demonstration for 300 cycles, was around 2 months of demonstration. And what you see in this particular graph is that indeed at the beginning, you capture completely the CO2. So the hydrogen is relatively high concentration. And then after a certain point, CO2, the sorbent is completely carbonated. So you have to, if you continue, what you will have is that CO2 is leaving the reactor. And at a certain point, you have the CO2 and the hydrogen, which are at the equilibrium of steam reforming, simply because the calcium oxide is completely carbonated. And then, of course, if you do the cycle part of the reduction, you have that at the beginning, hydrogen is consumed, CO2 is released, because you are increasing the temperature, and the calcium oxide, calcium carbonate becomes calcium oxide. And at a certain point, then all the calcium carbonate is calcium oxide. And we repeated this for 280 cycles. What you see here is that after 100 cycles, there is something happening on the system. So apparently after 100 cycles, the sorbent has some problem because the amount of CO2 that we can capture is lower. And indeed, when we opened the reactor, we found out that the sorbent was, the particle were breaking, and then some sorbent was reacting with the catalyst and then losing the activity. In any case, if we use this, those data to do a simulation of the reactor, and we optimize the reactor. And now, what you see here is that for many cycles, for, as I said, around 2 months, the system was working quite well. But what does this result mean? Is the system better than a steam reformer? To answer to this question, you have to do a techno-economic analysis. You have to see if the hydrogen that you produce is cheaper than the hydrogen that is produced otherwise with a conventional system. So what I want to show here is, first of all, that you have to do a techno-economic analysis, but I want to show also a particular case. So we take this system and we try to use this system for pre-combustion capture, and we evaluate what is the cost of this pre-combustion capture. And this is the table. And the table shows you that if you take a conventional system, you have a certain efficiency. If you take a conventional system with a standard CO2 capture, your efficiency decreases, but is, let's say, 47%. So this is our benchmark. And you see that with the new system, our efficiency is even lower than this. Now, this is just to say that if you don't do a techno-economic analysis, the results do not have much value. Of course, for other application like pure hydrogen production, the efficiency is higher than the conventional system, but I still want to show these bad results. So do not be afraid of showing the bad results, because in this way, the companies will not invest in something that we know that at the end of the day is not economic. Now, let me go to the second part. I told you that I want to show for the same system a membrane reactor connected with a chemical looping. And why I use a membrane reactor with a chemical looping is simply because in a chemical looping, like I showed you before for copper, you have the reaction with air, which is exothermic, and produce a metal oxide, and then this metal oxide you can use for different purpose. And one purpose could be that you do a fuel plus steam, and you have chemical looping reforming. So you produce CO and hydrogen. Now, if I take this again as a black box, you have air, you have fuel, you have CO, CO2 and hydrogen, and you have nitrogen. The nice thing is that nitrogen and CO2 are separated. So it's a way to supply the energy to the system without mixing nitrogen and CO2. Now, if I take this and I combine with the membrane, what I have is a so-called chemical looping membrane reactor. Now, what is this system doing is integrating the reaction and separation of oxygen and the reaction and separation of hydrogen. So again, if you make a black box, you have air, methane, steam, you have CO2, water, and nitrogen, but they are coming out of different outlets of the reactor. So you have pure CO2 with water, of course, you have pure hydrogen, and you have pure nitrogen, or at least nitrogen without CO2. So all in all, is very much integrated. And if you want to know the history, of course, you can look at the thesis of Medrano. Just to tell you, in 2012, we started with the idea. 2017, we did the TRL 4 to 5 demonstration. And to do this demonstration, of course, you have to do a working setup, relatively big. So here you see a few pictures. This is the air reactor. Then the solid have to move up, 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 be separated from the nitrogen, go in the other reactor where there are the membranes. Here there is the steam reforming, and then hydrogen is separated from the membrane from this side, and then the solid is going down again, and this continues recirculating. And I want to show a few experimental results. Those are the membranes that we use, are very thin palladium silver membranes of around 5 micron. You see that you need this very thin membrane because the separation of course, the flux through the membrane will increase the thinner is the membrane. Now, this is an experimental demonstration that we did. The first is the first 20 minutes, 30 minutes are the reactor with the membrane closed, so we are not extracting the hydrogen. What you see here is that the conversion is quite stable, the hydrogen production is quite stable, and if you make the calculation, this conversion is the equilibrium conversion for methane. So this is the minimum level of methane I can reach with this reactor in this condition. And then when I open the membranes, in this particular case, we had 3 membranes, the hydrogen decreases because I'm extracting the hydrogen, the methane is decreasing. So indeed, I reach an equilibrium. I reach a conversion that is higher than the equilibrium of the reactor without membranes, and the CO2 is increasing. So I'm converting more methane to hydrogen and CO2. What you see here is also a lot of fluctuation in a particular point of the reactor, and this is a sign that the solids are moving. So this is very important for us. When this temperature was very stable, there was no circulation of the solid, and then there was no chemical looping occurring in the reactor. Now, these are only a few experiments, and then if you take these experiments again, you can do the simulation. And what you have to do is a complete simulation of a complete system. So you have to take your membrane reactor and chemical looping, put together with the other components, and do a simulation. Another message that I want to tell you is that obviously when you do a techno-economic analysis, your product should be delivered also in the same conditions of the conventional system. Now, the conventional system, as I told you, delivers the hydrogen at high pressure. Since I'm using a membrane at the outlet of my reactor, the hydrogen is at low pressure. So if I want to be fair, I have to put compressors here, because otherwise my reactor looks nicer and cheaper than the conventional system, but it's not fully true because the compressors for hydrogen are very expensive. So another message, be fair when you do a techno-economic analysis and comparison. Now, if you do this, of course, what we use is Aspen. We also develop models for membrane reactors in Aspen, fluidized bed and packed bed, so we can change the membranes and do sensitivity analysis in Aspen. And at the end of the day, what is important is the cost. Now, if you take the conventional hydrogen production with steam reforming, this is the cost, and this is the efficiency. The cost, of course, depends on the cost that we put for methane inside the system and for electricity. So don't look just at the cost, look at the ratio between the cost. If you use the cost of methane in US, most probably this one will be 0.1 euro per cubic meter. In any case, if you take a conventional system, you can capture the CO2. If you capture the CO2, then of course the efficiency decreases depending on the amount of CO2 that you capture, and the cost will increase. And with the new system, the efficiency remains the same. The amount of CO2 that you can capture is up to 90% in this particular case, and the cost is very similar. So why is only 90% and not 100%? Simply because I'm using also the compressors, and I have to take into account the CO2 that is produced because I'm using electricity. And that's why the cost is not extremely lower than this, but is surely lower than a system with CO2 capture. Recall that here there is 90% CO2 capture. Of course, this is a simulation. We did some experiment. We have to be, again, fair that there are still some challenges. And the challenges come when you test the system for extremely long time. When you use membranes, you have to test for extremely long time, because in the first few 100 hours, all the membranes look very good. For palladium membrane, what you see here is that for 800 hours, it looks very good. After 800 hours, this selectivity drops to almost here. Still very good, but not enough to have extremely pure hydrogen. And why this drop is because there is something happening on the membrane, and we spent 2 or 3 years to find a way to operate this fluidized bed reactor with the membrane. And what we came out with, as I said, after 3 years of research, is a new kind of membrane where we have the support, we have the selective layer, recall palladium silver, and then on top of it, we put a protective layer. And again, this protective layer is a ceramic layer that makes sure that there is no contact between the solid, the copper, the nickel, and the palladium. And of course, you have to test it, and you have to test for a long time. And here is the proof. Now, 900 hours in fluidization with this different temperature change inside the reactor. And you see that a conventional membrane, this is the selectivity, stays okay for 400 hours. And then after 400 hours, the selectivity decreases, while the new membrane stays okay for 1,000 hours. Now, 1,000 hours is not nearly enough for making sure that it's interesting for industry. That's why in the new projects, we are trying to test those membranes for much longer, I will say in a minute. And finally, I promise you also the combination of heat and power. Again, heat and power production, or CHP, you can do in different ways. And the idea behind it is that if you do electricity production and heat production in the same place, then the efficiency increases. And if the efficiency increases, then the CO2 emission decreases. Now, we did several projects starting from refer cell, and we did several tests on the micro CHP system. And as micro CHP system, what we selected is a system where the electricity is produced by a fuel cell. And now if you take a fuel cell, then you know immediately where I'm going, because a PEM fuel cell needs hydrogen, but hydrogen is produced by natural gas. So all the vendors of this micro CHP system require natural gas and water, and they produce electricity and power. And of course, this is the same story of before. If you want pure hydrogen, then you have to have a lot of steps. Indeed, if you take a commercial system and you open, you have several reactors inside with a purification step. And what we do is converting this only with methane. Now, just to go a little bit faster, we have the conventional system and we go to a new system. What you see here is that the fuel cell is more or less the same, just a small change, but the big change is obviously in the production of hydrogen. Now it's only a single reactor with membranes. And if I divide this system in 4, just for a comparison, you have steam production, hydrogen production, fuel cell, and heat recovery. In the new system, steam seems similar, fuel processor is very different, fuel cell seems similar, and heat recovery seems very similar. And if I compare, what I found out is that the conventional system has an electrical efficiency of 34%. If you take all the systems on the market, you will see that the efficiency will range, the one that is declared, would range between 32 and 35%. So the model is catching quite well the efficiency. If you take a membrane reactor, the efficiency goes from 34 to 43. And what is the trick here is that if you use a membrane reactor, as I told you, you can shift the equilibrium, so you can have the same conversion at lower temperature. And this, for this particular system, means that instead of the nominal 830 degree, I can go with the same amount of hydrogen produced at 600 degree. And this jump in temperature gives a big jump in efficiency. Of course, I also have a single step instead of 4, and this gives me also some savings in terms of capex. But the OPEX, so the efficiency, is only due to the temperature that I can decreased from 800 to 600. And finally, just to show what we did in the last years, what I show you before is something ranging between 2012 and 2017. What we did, we start with a very small membrane. I recall the first membrane with selectivity of around 3, and then we found a way to produce multiple membrane in a reproducible way. Then we did the first real reactor working for a long time. So recall, the reactor has to work for a long time with very pure hydrogen. Then we increased the membrane, and we did bigger reactors and up to a design of 20 cubic meter per hour. And in pictures, this is the first membrane with the support. You see that slowly we increase to 10 centimeter, first small reactors, and then multitubular reactors still below 20 centimeter. Here, the first breakthrough, 1,000 hours, pure hydrogen production. Then we tried to scale up in a poor way, scale up. So we took 30 centimeter membranes and we put together. And then finally, we work on the scale up. In the meantime, we can put much more membranes, and we can have an increase of size of the reactor. You see that from a very small one to a big one, and even a bigger one. And as I said before, what we have to do now is to test the membrane for a long time. So here you see a lot of ongoing projects. MEMBER, which is combination of palladium membrane and sorption enhanced reactors, up to Macbeth, which is the biggest project where we produce 2 prototypes and test the 2 prototypes for 1 year, so 8,000 hours continuous operation. And this will be the last step before we go to real commercial systems. Here, a few more projects, and in view of time, thank you very much.
Thank you, Fausto. Congratulations for an excellent talk as well. I will check the audience if there are some questions there. You can raise your hand. Andrei.
Hello, colleagues. I have a question. Thank you very much for a very impressive presentation. The question may be about the very end of your presentation about commercialization. So I don't know how to ask. How do you evaluate? Is it a technology for tomorrow, for today, or day after tomorrow? So when do you expect it to be really commercialized in a wide scale?
Okay, so this is a very nice question. The answer is that it depends on the application. For small scale application, we already created a spin-off company, which is now working on the scale up of the production for the membranes. So for, let's say, between 50 and 300 cubic meter per hour of hydrogen, basically is almost today. So the company is busy making the commercial units, and hopefully this year or early next year there will be, you can even order and buy it. If you are looking at larger scale, we have to still wait for the big projects to deliver stable performance for 1 year. I expect that in that case, within 5 years, we can have much larger units if we prove that the membrane work for at least 1 year. Why I say at least 1 year? For 2 reasons. One is that, as I said, with membranes, unfortunately, you see the problem when you test for a long time.
Yes.
And the second one is that in all the techno-economic analysis we took, we put 2 years as minimum lifetime of the membrane. So if that is reached, then the number makes sense. On the other hand, if you have to change the membranes every 6 months, then of course the numbers are not as nice as they look now. So the cost will increase.
Thank you.
Thank you, Andre. Do you have questions from other people? Maybe then one last. So impressive for the hydrogen work, I would say. But what's next? I assume that you also are looking at other systems, Fausto.
Yes, some of the projects that I show you are, for example, for hydrogenation of CO2. Of course, we use different membranes in that case. You need membranes that are either selective for methanol or for water, rather than for hydrogen. Our work will be mostly on hydrogenation. If we look at high temperature operation, the next step will be to use the same type of membranes, but for dehydrogenation reaction, like propane, butane dehydrogenation, where the product is not hydrogen per se, but is helping the reaction. Removing the hydrogen is helping the reaction. And if you look at lower temperature, we are working mostly on bio-based reactions, where again, removing one of the products can help the lifetime of enzymes, for example, or bacteria. So these are the two main areas we are working at the moment.
Indeed, this will keep you busy for a while, I would say. So
yeah.
Okay, so let's thank our speaker again, and big
thank you again.
virtual hand. Thank you, Fausto, and I will give you a real applause then. And I will see you soon. Okay.
Thank you.
Thank you, everybody. Thank you for participating in this session. And a special thanks, of course, to our speakers, which did an incredible job. Thanks, and see you soon. Bye-bye.
And thanks to you, Kevin.
Bye-bye, Andre.
Bye.
Okay, hello, good afternoon, everybody. Can you hear me well?
Okay.
Okay.
I'm ready.
Wonderful. Okay, then let's get started with this afternoon's session with two keynote lectures. And so my name is Hans-Jörg Freund. I'm from TU Dortmund University, and I have the pleasure to chair this session, these two talks. And the first talk will be given by Professor Vladimir Arutyonov. And Professor Arutyonov, it's a difficult name. I hope it's correct.
Okay, everything is all right.
Is from the Semenova Federal Research Center for Chemical Physics at the Russian Academy of Sciences in Moscow. And I will briefly introduce Professor Vladimir Arutyonov. He is the head of the laboratory for oxidation of hydrocarbons of this Semenova Federal Research Center for Chemical Physics of the Russian Academy of Sciences. And his research interests cover the kinetics of gas phase reactions, oxidative conversion of hydrocarbon gases, environmental problems of energy and transport, and also sociological problems of science. And when studying these kinetics of thermal gas phase processes, particularly of sulfur dioxide reduction with methane, acetylene, hydrogen, H2SCO, kinetic models of all these processes and reaction products and the dependence of their composition on the initial ratio of these reagents were proposed by Professor Arutyonov. And he pays great attention to the study of these oxidation processes, particularly of low sulfur natural gases. And he is author of more than 300 publications and 24 patents. And we are now very much looking forward to the talk on non-catalytic gas phase oxidation of hydrocarbons. And now the floor is yours, Professor Arutyonov.
Thank you. I'll make a screen. Excuse me. Excuse me, demonstration screen and full screen. Пока слайды сначала. Can you see the screen, my presentation?
No, we see you.
Oh, excuse me. Excuse me. Okay.
Владимир Сергеевич, там переключиться в эту демонстрацию экрана.
Сейчас. Я нажал демонстрацию экрана, так.
Ну, по идее, вы должны тогда уже, тогда мы должны видеть фон.
Вот это выруби. Не-не-не. Так, вот запусти.
Теперь хорошо.
А вот теперь нажми на полный экран.
Сейчас пока слайдов. Сначала. Okay, you can see the full screen, yes?
Yes.
Thank you. I begin. Chairman, colleagues, the title of my lecture is Non-Catalytic Oxidation of Hydrocarbons. It is evident now that the last century was the century of oil and, of course, petrochemistry, due to abundant resources of oil and relatively simple destructive processes of oil refining, such as cracking, pyrolysis, hydrogenation, isomerization, and so on. But it is also evident that this century will be the century of natural gas and, of course, gas chemistry through the abundant resources of unconventional gas resources, such as, first of all, gas hydrates, which composite up to 1/2 of the total organic carbon in the Earth's crust, and these resources approximately 100 times exceeded that of proven natural conventional natural gas resources. But excuse me, to use these huge and conventional natural gas resources, it is necessary to have cost-effective technologies for their extraction, transportation, and first of all, chemical processing. Several notes must be made. First of all, gas chemistry is a petrochemistry, but based on methane. It is its fundamental difference from traditional petrochemistry lies in the constructive direction of its processes. The goal of gas chemistry is to obtain from the most stable hydrocarbon molecule CH4 the entire scope of more complex and, of course, the less stable petrochemicals. And the conversion of methane into thermodynamically less stable products requires a lot of energy. It's a principal difference between gas chemistry and petrochemistry. And the most accessible and inexpensive source of this energy is the oxidation of methane itself. Therefore, the most effective method of energy supply is autothermal processes, because they let us to overcome the necessity of have very expensive heat exchangers, metal intensive heat exchangers, and let to overcome the inevitable heat losses if we use heat exchangers. There are only very limited number of substances which can be produced directly from methane. First of all, it is carbon black and hydrogen, ethylene, acetylene, methanol, formaldehyde, but the most important substances which we obtain from methane is syngas. This route from syngas led us to obtain practically all other petrochemical products which we usually obtain from oil. But this road is very energy intensive. It proceeds at a temperature approximately 1,000 1000 centigrade, and of course it needs a lot of energy. Modern industrial technologies, gas chemistry now is a major technology with very huge enterprises, but it is very complex and very costly, very expensive processes. The current huge enterprises, we need to have capex as high as approximately $200,000 per each barrel of final production, which is approximately 10 times higher than usually in petrochemistry. Therefore, we need more inexpensive and more efficient processes for gas chemistry. There are two principal technologies, the two principal directions for increasing the efficiency of gas chemical technologies. One direction is increasing the efficiency of syngas production, and the other is increasing the efficiency of direct methods that do not require syngas production at all. Among syngas production, there are many interesting technologies now are developing: oxidation of ceramic membranes, macrochannel reactors, short-time catalysis, but up to now, no one of these technologies has reached the industrial level. We will discuss below a matrix conversion of hydrocarbons to syngas, because first of all, it's technology which we're developing ourselves, and on the other hand, because we consider that is one of the most promising modern technologies. Among direct methods, of course, the most popular is oxidative coupling of methane, halogenations and oxyhalogenations, partial oxidation of methane to acetylene, but we will speak only about direct oxidation of methane to methanol and selective oxycracking, which they possible because these methods let us to obtain alternative GTL route for obtaining products. About matrix conversion of hydrocarbon to syngas. It is based on partial oxidation of methane to syngas, but partial oxidation needs a very low portion of oxygen with so-called oxygen excess coefficient alpha. Here is coefficient alpha as low as 0.25. The heat release at this reaction is very low. It is insufficient for a stable proceeding of this reaction. Therefore, we need a parallel reaction of complete oxidation, some part of methane to oxidize completely to CO and water, CO2 and water, which let us to obtain necessary amount of energy. And it is necessary to make this oxygen excess coefficient alpha as low as possible, and matrix conversion provides us possibility to work not with alpha as low as 0.25, but as low as 0.34-36, which led to obtain significantly high yield of syngas. The idea of matrix conversion is simple enough. We recuperate some part of heat which contains obtained syngas back to the fresh gas mixture. To recuperate, we use to make this recuperation. It is possible to fabricate a closed volume, matrix closed volume, fabricated. Excuse me. Fabricated from penetrable heat resistance, any penetrable heat resistance material, and intensive convective, and we can organize so-called surface combustion near the inner surface of this chamber, and intensive convective and radiation heat recovery from conversion products from the combustion front to the walls of this chamber and then to the fresh reagents, led us to recuperate significantly part of the heat. Thus, it is possible to significantly widen combustion limits, especially for the rich mixtures. Here you can see that it is a very compact, very small device. Here is experimental installation with a capacity of about 2 cubic meters per hour. Here is, you can see internal construction of this device. The matrix volume is constructed by 2 flat matrix, round flat matrix, situated one against other. Gas mixture, fuel and oxygen introduced symmetrically from both sides, and after combustion near this inner surface, obtained syngas get out upwards. It is possible to operate both with atmospheric air, enriched air, oxygen, and operation with atmospheric air led to obtain stable conversion at low enough oxygen excess coefficient alpha, such as 0.3436, providing syngas content up to 40%, approximately 25% of hydrogen and about 13% of CO. The conversion of both reagents approximately complete, and very important ratio hydrogen to CO is at a level of 1.6, 1.8. The main advantages of such a process, first of all, it's autothermal process, which needn't no additional energy or heat. It leads to processing hydrocarbon gases practically of any composition, even very rich hydrocarbon gases, associated gases, high range of possible capacities. We have seen that very low capacities is possible, compactness, because specific volume capacity approximately at any rate 10 times higher than for steam reforming. Simplicity in construction and operation, and of course absence of catalyst, which significantly reduce the demands to gas preparation, for gas preparation. It's also possible to work with enriched air or with poor oxygen, and as we decrease the concentration of nitrogen in oxidizer, we increase the concentration of hydrogen and CO, and it is possible with at work with hydrogen, it's possible to obtain hydrogen concentration as high as 45%, and even more, and CO concentration as high as 31%, with this ratio at a level of 1.7, 1.8. On this slide, you can see two demonstration installations. This one with capacity up to 20 cubic meters per hour. This is for work at atmospheric pressure, and this one to work at enhanced pressures up to 10 atmospheres. As a material for matrix fabrication can be used any heat-resistant penetrable material such as perforated ceramics, metal foam, but we prefer now to use pressed nichrome wire or Fechral wire plates, which most convenient for construction for real devices. Several words about advantages of using nitrogen-containing syngas, which can be obtained by oxidation with atmospheric air. First of all, it is very cheap syngas. It is uncostly process to obtain syngas. The second most important advantages is the safety of operation, because we do not need any oxygen, which practically it is impossible to use oxygen in the field condition. There were several industrial scale experiments in pilot plants, which show that it is possible to convert up to to have a conversion of CO up to 50–60% per pass to reactor, and they use syngas of this composition, which practically just the same composition of syngas which you obtain at matrix conversion. Therefore, using matrix conversion with atmospheric air, it is possible to obtain to construct pilot plants which can be operated directly on field conditions. Matrix conversion allows to utilize very small gas sources such as biogas. It's possible to have biogas oxidized by air just on the site, and then with Fischer-Tropsch synthesis obtain liquid fuels. Matrix conversion opens the possibility for simple small capacity production of hydrogen. It led us to bypass such complex and doesn't resolve up to now problems as storage and distribution of large amount of hydrogen. To obtain maximal value amount of hydrogen, it is possible to combine matrix reforming with subsequent steam reforming of CO, thus obtaining gas with a concentration of hydrogen up to 70%. Here you can see such demonstration installation. And in this table, you can see that it has significant advantages before steam reforming. Specific volume capacity approximately 20 times higher. Fuel consumption per 1 cubic meter of converted gas approximately 4 times lower. Only one catalytic stage. The process is autothermal. Significantly lower consumption of steam and practically the same concentration of hydrogen in obtained gas, in final gas. This matrix conversion also opens the possibility for small capacity production of methanol. Our experiments have shown that it's possible to have conversion per pass up to 20% at relatively low pressures, with an CO conversion of up to 20%, and methanol concentration in product up to 90%. Significantly reduction of water consumption and significantly reduction of consumption of fuel gas. Therefore, it's open the possibility to significantly reduce the carbon footprints of production of methanol or production of hydrogen using matrix conversion. It's a real possibility to reduce carbon footprints of these processes. Very important process proceeds inside of the reactor. Kinetic modeling revealed the 3 characteristic stages of the methane matrix conversion. Here is a logarithmic scale. Therefore, there are very short stage of oxidation itself. Then the stage of thermal pyrolysis of residual methane and residual hydrocarbons, and with the production of acetylene, first of all, and then the stage of steam and dry reforming of products. And at this third stage, significantly increase of hydrogen yield and CO yield can be obtained. And as our calculations have shown, there is no direct interaction at this temperature, and in the absence of catalyst, there is no direct interaction of steam or CO2 with hydrocarbons, but the process proceeds through preliminary pyrolysis of hydrocarbons into acetylene, and then acetylene interacts with water vapor and carbon dioxide. Therefore, this opens to increase the yield of syngas by utilization of additional CO2 from the site. That is one of the additional way of utilization of CO2 from other sources, or to reduce to decrease the CO2 emission in this process. I have little time, so only several words about direct technologies. Here are the four most interesting direct technologies of partial oxidation based on partial oxidation of natural gas. Very interesting process, of course, is the partial oxidation to acetylene, and I foresee a very bright future for this process, but we do not ourselves study now this process. And three other processes are listed here. It is direct partial oxidation to methanol and CO, partial oxidation of selective oxycracking or selective oxidation to ethylene and CO, and of course oxidative coupling of methane, which also give us acetylene and CO. These three products, main products, methanol, ethylene, and CO, let us to suggest an alternative GTL road. In the traditional conventional GTL, we have three stages: syngas production, Fischer-Tropsch synthesis, and hydrocracking. Here we have two stages: oxidative conversion of hydrocarbons with obtaining these three products, and their subsequent catalytic carbonylation using platinum group catalysts, with a possibility of obtaining a significant number of valuable and demanded products. Such processes are very useful, especially for processing of refinery gases. You know that usually several billions cubic meters of such gases flared all over the world. These refinery gases contain saturated, unsaturated hydrocarbons, carbon oxides, hydrogen, and some other components. And after oxidative cracking of such gases, it's possible to obtain ethylene, CO, and hydrogen, and thus we can possibility to have catalytic hydroformylation or carbonylation with obtaining valuable products. Here, this table only shows that these catalytic processes are well developed, so we needn't to invent any special processes. We can use already existed processes. And the main advantage before traditional conventional Fischer-Tropsch is that significantly higher selective activity of catalysts for these products, approximately 2 orders of magnitude, and of course significantly lower capital costs. Several words about possibility of use selective oxycracking for processing associated petroleum gases. Up to now, 150 billion cubic meters of APG flared all over the world in all countries, in Russia, in the USA, in all countries. And this gas is impossible to use as fuel because they have a very high content of heavier hydrocarbons. Selective oxycracking in mild conditions leads to completely convert all hydrocarbons without touching methane itself. And the main products of this conversion is ethylene and CO. You can see that it's possible to significantly decrease calorific value of this fuel, which is necessary, and increase methane number, that is obtain fuel suitable for gas piston engines. And very promising, one more very promising group of processes is which is up to now practically undeveloped, is oxidative pyrolysis of hydrocarbons and conjugated oxidation of saturated and unsaturated hydrocarbons. Here you can see that oxidative pyrolysis of propane lets significantly increase the yield of propylene in comparison with usual thermal pyrolysis, and significantly decrease necessary temperatures. And here you can see that conjugated conversion of propane and ethylene leads to increase the yield of propane in this slide. Concluding, I want to say that non-catalytic oxidation of hydrocarbons allows us to develop a number of new processes for monetization of natural gas, including such kinds as APG, small scale and remote resources. And here you see my young colleagues which obtained all these results, which is told today. Thank you for attention.
Thank you very much for this very nice presentation, Professor Arotionov. And so the floor is open for questions. We do have time for a couple of questions. Maybe I can start with the first one. So regarding this matrix, you showed different structures and materials. Can you talk a bit about, are there any selection criteria? So of which kind, you know, of matrix you take? What are the most important criteria for doing this?
The only criteria is not heat resistance, because the temperature is not very high, up to 1000 centigrades. So because process proceeds not on these materials, but after these materials in gas phase, there is no cooking formation, there is no catalytic processes on material itself. Therefore, it's practically doesn't matter the composition of this material, only heat resistance.
Thank you. Are there any further questions from the audience? I don't see any hands. You can just open up your microphone if you have a question. Please go ahead.
Okay.
But I think maybe there are no further questions here. So what is the perspective of this technology for the next steps? Let's see. Where do you see the next application? So you're about to transfer this to some, let's say, larger scale industrial applications, or what do you think?
I think that there will be several applications. First of all is production of hydrogen and syngas. I believe the most important for metallurgical process, because they need cheap and cheap syngas with not hydrogen with not very high with not high purity. So first simple. If we speak about energetic using energy, we need for fuel cells, of course, we need to purify this hydrogen. But I believe that low scale production of hydrogen just on site of their consumption will let us to significantly bypass the problem of storage and distribution of hydrogen. It's a problem which have no practically decision for this problem, solution for this problem. So I believe that low scale production make it possible to use hydrogen just on site, produced from net gas, from propane butane fraction, from liquid. Our technology let us to use even light liquids, hydrocarbon liquids, to produce gas just on site.
Yeah. Okay. Thank you very much for this exciting topic and this very nice talk.
Thank you.
So we thank you, Professor Arotionov. And if you could now stop sharing your screen so we can then move on. Thank you again. So we will move on to our next speaker. The next speaker is Professor Zabelich. I hope I got this name correct. And he is also online. Okay, there he is. Hello, welcome to your keynote presentation. And I will briefly introduce Professor Zabelich. He is currently professor at the University of Michigan in Ann Arbor. And he received a Bachelor of Science in Physics and together with a Bachelor of Science in Mathematics and Chemistry from Western Chester University in Pennsylvania. And then he moved on to the University of Delaware, where he studied surface chemistry and catalysis, and he did his master and PhD there. And afterwards, he was actually in Germany at the Fritz Haber Institute of the Max Planck Society, working in the group of Professor Matthias Scheffler. And then he started his independent scientific research career, his faculty career in 2004 at the Department of Chemical Engineering at the University of Michigan in Ann Arbor, where he is currently the class of 1983 faculty scholar professor of chemical engineering. His research interests are quite cover a wide spectrum and include a lot of different topics, but the program is mostly focused on heterogeneous catalysis and surface chemistry in different areas, ranging from selective oxidation to hydrocarbon reforming, electrocatalysis, and photocatalysis. And for this, the LIGNIN-RICH group applies first principle theoretical approaches, but also various experimental tools to study chemical transformation on surfaces. And the central objective of this work is to get predictive theories of surface chemistry related to heterogeneous catalysis and also electrocatalysis and photoelectrocatalysis. So with this, I would like to hand over to Professor LIGNIN-RICH. His talk will be given on physical chemistry concepts of chemical energy conversion. And now, Zuyo, the floor is yours.
Thank you so much for such a nice introduction. It's unfortunate we couldn't meet in Italy. I was really looking forward to it, but it wasn't meant to be. So hopefully there will be some additional opportunities. So today I'm going to discuss some of ongoing work in my research group, where we are trying to understand how to use the solid oxide membrane reactors coupled to a catalyst to perform this direct methane conversion to the C2 products. So oxidative coupling of methane is a process that has been proposed about 40 years ago, and in this process, oxygen is used basically to react with methane to form C2 products, mainly ethane and ethylene. And there is a significant interest in this process that has been outlined in many talks because of the access to natural gas and our desire to convert the methane into gateway chemicals that can be used in petrochemical chemical industry. So the kind of a sequence of elementary steps that has been proposed for this process involves stripping of hydrogen by an oxygen atom on a metal oxide catalyst. This CH3 radical then reacts in gas phase, forming C2H6 products and then further C2H4 products. And the byproduct of this process is a formation of water. There's a number of questions or problems associated with wanting to do this process catalytically. And the first one, an obvious one, is that thermodynamics is very unfavorable. So if you calculate the free energy of reaction for this process at standard pressures and temperatures of interest under we can activate a CH bond in methane, you quickly realize that under stoichiometric conditions, there's a strong thermodynamic driving force to completely oxidize methane and form CO2 and water products. And you also have desire to form CO and hydrogen. And then after that, you can form the desired products, which are really C2 products. So essentially, there's no thermodynamic window where the production of C2 products is preferred. And we have also now calculated here in this graph carbon product selectivity as a function of oxygen to carbon ratio. And what you see is if you have low oxygen to carbon ratio, thermodynamically preferred product is solid carbon. As you increase this oxygen to carbon ratio, thermodynamically preferred product is CO. And then as you increase it further, you go to CO2. So this is a significant challenge because in order to overcome these thermodynamic limitations, you have to design catalysts that push the process very far from where it wants to go thermodynamically. Another significant problem with this process is that gas phase O2 which is fed with methane, for example, in plug flow reactor, is involved in non-selective deep oxidation pathway. So there's a really interesting study published in 2019 in ACS Catalysis Journal, where it was demonstrated, I think very conclusively, that gas phase oxygen is actually involved in these unselective products that lead you all the way to CO2 and water, to these undesired products. So this fundamental challenge with reaction pathways manifests itself in a kinetics of this reaction, where the reaction rates to production of CO and CO2, the undesired products, in general have first order dependence in oxygen. They prefer higher partial pressure of oxygen, while the rates of formation of the desired C2 products have a half an order dependence of oxygen. So in general, you would expect higher C2 selectivity to be achieved at lower oxygen partial pressures. So when you consider these challenges with thermodynamics of the process that I discussed in the previous slide, and with the kinetics of the process and reaction pathway that I'm showing on this slide, it's really not surprising that we have not been able to design a catalytic material that can give us a high selectivity with high conversion for this process in a packed bed reactor. So we've tested many oxide catalysts, and in general, there's an agreement that there's really no material that reaches the desired techno-economic target area, and the techno-economic target area is to reach about 90% selectivity to C2 with the CH4 conversion of about 40%. And what you see here is that most of, or almost all materials or oxides that have been tested fall on this kind of line, where you can either have low conversion with high selectivity, or if you are able to accomplish high conversion, you have a very limited selectivity and you're not even close to this techno-economic target. So just to summarize the main concepts here, so gas phase O2 is involved in non-selective deep oxidation pathways, and higher C2 selectivity is expected at lower partial pressure of oxygen. So the question is, if we move from this packed bed reactor to something that looks like this, a membrane reactor, where we allow oxygen to be introduced into the reactor along the length of the reactor and encounter methane on the other side of the membrane, where the oxidative coupling reaction can happen, would we be able to, in principle, use this design to overcome these limitations associated with reaction pathways, mainly the bad role of gas phase oxygen and the reaction kinetics, mainly manifested in these differences in reaction orders, and achieve higher selectivity toward the C2 products. So when we got into this, we actually perform a very simple analysis where we analyze the behavior of a packed bed reactor and membrane reactor subject to the same operating conditions and the same catalyst, and we try to understand what difference this introduction of oxygen along the side of the membrane reactor makes. So here we show results of this modeling. And again, the rate laws and kinetic parameters for these kinetic studies were taken from this paper by Stanch et al. And they mainly refer to this oxide catalyst that I have here. The results that I show here are for stoichiometric feed or C2, H4 to oxygen of 4, and relatively reasonable temperature for this process. And what you see here is that if you're operating this process in a packed bed reactor, you get a performance that's actually not very good, because your yield is well below techno-economic target and your selectivity is low at the given conversion of about 30%. On the other hand, for a given set of identical conditions and identical catalysts, as long as you can bleed that oxygen through the sides of this packed bed membrane reactor, you can achieve much higher yields with much higher selectivity and a much higher conversion, subject to this kinetics published in this paper here. So if you think about designing a membrane reactor for this kind of oxidative coupling system, you really have to think about a membrane that can, as I said, bleed oxygen and introduce it into the reactor and prevent that evolution of oxygen into gas phase oxygen species, which then can react within the gas phase with methane fragments to lead you to these undesired oxidation products. So the membrane that we focused on is a solid oxide membrane, where oxygen is delivered to the catalyst in the form of O2- ion that comes from the solid oxide material and is spilled over to this catalytic material that's performing oxidative coupling. So we want to have a membrane that can conduct O2 minus. We want to have on top of that membrane a porous catalyst that gives us a high surface area that can also conduct O2 minus and bring it to the surface of this catalyst where these reactions can with methane can take place. And membrane and catalyst need to be compatible with each other in the design. And what this means is that they have to be not reactive with each other at high temperature processing at which this membrane would be designed. And also they have to have a similar thermal coefficient of expansion, because if you have a different thermal coefficient of expansion, that's going to lead to the different to the gradients and strains here, which is going to cause your membrane to rupture and therefore allow for leaking of oxygen or methane through this membrane. So these are kind of criteria that we had to select and identify membrane catalyst systems that would test in this membrane catalyst reactor design. And to identify which materials actually lend themselves to this criteria, we went to literature and we looked at the materials that have been used in packed bed for oxidative coupling of methane and that have shown reasonably high conversions and reasonably high selectivities. And in general, what we found, and this was published very nicely in this paper from 2019 by Zabelich and Professor Schrogel group, and they found that in general, the materials that have these four elements tend to be a good performing materials in oxidative coupling of methane. So we focused on oxides that contain these four materials because the idea is that they can give us high selectivity and relatively high conversion. Again, we want to couple these catalysts with membrane that can conduct O2 minus ions. So we again looked through the solid oxide membrane literature and looked for these membranes and found the membranes that can conduct O2 minus ions and that contain these elements that I show here that give us high selectivity to C2 products as oxidative coupling. So we, using this process of, or this criteria, we arrived to a set of 5 perovskite oxides that seemed promising for this process from perspective that they can transfer O2 minus ion and that they should give us high selectivity and high activity in oxidative coupling process. And these perovskite oxides are LSGM, LSM, LSCF, BCG, and BYS. So the first step was to test these perovskite oxides in a plug flow system and really establish whether they can give us high selectivity with reasonably high conversion in oxidative coupling of methane. And what I show here are the results of these testing. The testing is performed at relatively standard conditions for this process. And what you see here is that LSCF and LSCM actually gave us a very poor performance. We could not get much selectivity at almost any conversion of CH4 over these materials. On the other hand, BCG and LSGM gave us a reasonably good performance, kind of standard performance associated with the best oxide electrocatalysts or catalysts that have been used for this process. And what you can see that these materials, BCG and LSGM, gave us high C2 selectivity at low partial pressure of oxygen. And if you're operating a membrane system, you would expect that your partial pressure of oxygen across the entire system is lower compared to the, for example, entrance of a plug flow system where you have a high pressures of oxygen. And then we attempted to basically investigate whether we can integrate these BCG and LSGM systems in a membrane system. So the first step was then to kind of look at the stability of these systems over a longer period of time. So this is now a stability test of LSGM material in oxidative coupling of methane. These are the performance, yield, selectivity, and conversion. You see that's relatively stable over the period of the experimental test in our laboratory. There's no significant changes in the performance. These are the XRD patterns associated with these materials, these LSGM oxides. And what you see is that the material that we start with in terms of its XRD diffraction pattern does not change at all compared to the material that we finish with here. So in general, what we see is that this LSGM material tends to be relatively active, selective and relatively stable under these conditions. We made similar observations for the BCG material. So this is now the performance of a BCG material as a function of time. And again, you see that the stability of this material is relatively good. You don't see dips in conversion or selectivity over time. And the yield to C2 products is also relatively stable. This is the XRD patterns before for the fresh BCG and after for reacted BCG. And what you see here is the appearance of additional phases that have to do with the presence of carbon dioxide in the product stream, and this carbon dioxide tends to react with BCG in a way that it compromises it, that you create certain additional phases in this BCG. But nevertheless, this was not done at the expense of the stability in the performance. So just to conclude this section on the catalyst screening, so basically we identified the LSGM and BCG as promising materials that can be used as catalyst for oxidative coupling of methane and as membranes to conduct O2- to the active site that participates in this oxidative coupling oxidative coupling process. We showed that these identified catalysts are selective to C2 products at the high C2 to oxygen ratio. They're ironically conductive and they're relatively stable at reaction conditions. So the next step was to try to introduce these materials in a membrane catalyst design, in a membrane catalyst system. And our membrane catalyst system looks something like this. So we have a membrane, again, which is made in this case of LSGM. And then we have a porous catalyst, which is also made of LSGM. And the idea here is to transfer O2 ions from the air side, react them on the catalyst with methane to form desired products. In the case of LSGM, since the electron conductivity is very low, the O2- ion conductivity is also low. So to enhance this conductivity of O2- ions, which is limited in principle by electron conductivities, we impregnating the membrane with nickel, and nickel allows us then to have a more electron transfer and therefore more O2- transfer. In the case of BCG, we really didn't have this problem because BCG can conduct electrons and O2- relatively well, and we can introduce BCG membrane, and on top of that, again, design a BCG porous catalyst for this process. So the first step was to test these materials in our bottom cells, or bottom membrane cells, which are relatively easy to design. So in this design, you basically create your membrane material, you pellet press it, you sinter it, and then you coat that membrane with a catalytic material again. And we focus on nickel LSGM membranes with LSGM catalyst on top of it, or BCG membranes with BCG porous catalyst on top of that. So this is now some characterization of these bottom cells. These are cross-sectional images of the materials. And what you see here is this porous membrane material. This is nickel LSGM. And on top of that, or this is a non-porous membrane material, I should say. And on top of that, you have a porous catalyst layer that's containing LSGM. If you zoom in, you see this interface between the membrane and catalyst. That's relatively obvious. And also, if you do some elemental mapping, you see these pockets of nickel, which are allowing you to conduct electrons through the membrane more readily, and therefore O2- transfer is less impeded. In the case of BCG, we have a similar situation. We have a porous membrane or porous catalyst on top of the non-porous membrane. And again, if you zoom in, you see this catalytic material that is sitting on top of this membrane. So we tested these bottom cell membranes under these reaction conditions that I show here, and we are moving a high concentration of methane with very little amount of helium. So this is not diluted stream that we are testing, and our setup looks something like this. So methane and helium come from this side. They encounter the porous catalyst on top of the membrane. Air is used as an oxygen carrier, and this O2- from air is transferred through this membrane and encounters methane on this catalyst side, and that's where the oxidative coupling process takes place. So these are now the results of some of these studies. So this is now LSGM system. And what you see here, that under these conditions that are essentially starved of oxygen, where you're running, where you're getting oxygen from that membrane side, the stability of this LSGM system is not very good. So you see that over time, the performance of this material declines as a function of time. On the other hand, what we see is that under identical set of conditions, this BCG system that contains BCG membrane and BCG catalyst actually is relatively stable. We also did some studies looking at the, what is the cause of this lack of stability of this LSGM system. And these are now XRD patterns of LSGM catalyst before it was reacted. This is after it's reacted, and what you see is the presence of these peaks, XRD peaks that correspond to formation of graphite. So we postulated that under these conditions that are where you have a very high C to oxygen ratio, there's a formation of CC bonds on this LSGM catalyst, which leads to the formation of graphitic carbon, which starts to affect performance after a certain period of time. In the case of BCG, we really do not see the presence of that graphitic carbon. And this is also supported by our Raman studies. So I show here a Raman spectra of a synthesized LSGM material, and you see that used LSGM material has these peaks that are consistent with the formation of sp2 carbon, mainly carbon D band and carbon G bands, which tells us that we are forming this carbon on this LSGM material. On the other hand, in the case of BCG, we see that the material is actually relatively stable and clean of carbon even after an extended period of time on stream, which is kind of surprising because, again, we are operating at a very low carbon to oxygen ratio because oxygen is delivered to this membrane, and there's a mass transport limitations to deliver oxygen to that active site. So this picture of carbon affecting our performance of LSGM is also supported by this elemental mapping after the reaction. So this is now LSGM catalyst before the reaction. These are elemental mapping, the elements you see here. And you see that after the reaction, you see some morphological changes to the catalytic system, but also you see significant formation of carbon as characterized by this red color that I show here. On the other hand, BCG catalyst keeps this morphology relatively steady over the course of experiment. And furthermore, we do not see significant amount of carbon that's detected on this catalyst after this reaction. So the question that we asked is, why is BCG so much more stable compared to LSGM? And the answer that we came up with is that really this has to do with the oxygen flux through BCG, which is significantly higher compared to LSGM. It's a better conductor of oxygen. Therefore, you have a more oxygen that's coming to the surface and therefore burning off that carbon. And also it's a more reducible oxide compared to LSGM. So here we show hydrogen temperature program reduction, suggesting that the BCG experienced reduction at a lower temperature, and there's much more oxygen that is used in this reduction process that evolves from the same amount of catalyst compared to LSGM. So I'm going to conclude this. So this is still work in process, and what we are doing now is we are extending this into the tubular kind of membrane reactors. We're trying to understand whether we can reproduce these results that we kind of stimulated this discussion with of modeling, where this BCG catalyst in tubular system actually should give us performance that are approaching these techno-economic targets. So I've discussed advantages and challenges associated with membrane catalyst system. I've demonstrated that the membrane design appears to be favorable due to several advantages brought about by the lack of gas phase oxygen. We've tested the number of oxide catalysts which show high selectivity at low oxygen partial pressure. And carbon-induced deactivation is a major issue here because you're operating at the low carbon to oxygen ratio, and it appears that this BCG perovskite material shows higher carbon tolerance compared to the other materials that we have tested. So with this, I'm going to conclude, and if there's any questions, I'm more than happy to try to answer.
Thank you very much. I give you a clap, a virtual clap hand for this very nice presentation and this very nice overview on the membrane catalyst reactor systems. And I think we do have time for a couple of questions. And again, I ask the audience to put the questions. You can either raise your hand or just open up your microphone and pose your question, please.
Excuse me, please. I cannot find the button to raise the hand, but...
You can just go ahead. It's okay.
Okay, thank you very much. Thank you very much for your very interesting presentation, very interesting results, very challenging. My name is Mikhail Senev. I'm sitting next to Professor Arutyunov in the Institute of Chemical Physics, Moscow. And I have a question about the selectivity. There are two major problems with the selectivity. One of them is just a kinetic. No matter how high or low is oxygen partial pressure, if you go to higher conversions of methane, to higher concentrations of your target product, you will still have a strong decrease of the selectivity, just due to the difference in reactivities between the target product, ethylene, and initial reactant methane.
Yeah,
so,
this is a standard A goes to B goes to C, where B to C has a higher rate constant than A to B.
Yeah, right. So, is it possible, to your opinion, to fight with this problem using membranes? And the second question, I will ask both at once. If you show us. You showed us the results you obtained at higher conversions. There is, if I'm not mistaken, selectivity about 45–50%. How do you plan to fight with the high heat release in the case of such a low selectivity? Thank you.
Yeah, so this is this problem of A goes to B goes to C is a kind of classical problem that we face in many of these partial oxidation processes, and this is part of the reason because we want to go to the plug flow. We have a better mixing with respect to the outcome of that particular problem and see how far that's going to get us. Having said this, I think you are absolutely right. I think this is an extremely challenging problem in terms of pushing that selectivity to a higher number. Now, the good thing about if we can pushing selectivity, then this problem of heat release becomes a little bit less challenging because you're releasing less heat as you go to a less thermodynamically stable product. So to me, the answer to this question is, and I try to kind of say this, you can use catalysis to push away from thermodynamics to a degree. But you cannot use catalysis to completely overwhelm thermodynamics, which is extremely bad in this particular case. So I think the solution will require finding maybe better catalyst than BCG. Maybe there's something out there that can be better. And then using this kind of reactor design schemes that can allow us to fight that the problems that I've discussed in terms of kinetics, in terms of reaction coordinate or mechanism.
Okay, thank you. Do you have any idea about the better catalyst?
No. Do you?
Not yet. Thank you. Thank you very much. Thank you.
Thank you very much. Are there any further questions from the audience?
Let me. There are two questions. First, what actually limits your specific reaction rate? Is it conductivity of the membrane or activity of the catalyst surface?
So in this particular example that I showed, it is the conductivity of the membrane. But we have now been able to design thinner membranes that actually conduct O2 minus relatively well. And the secret here is really you want to get a matching of the rates of CH bond activation and O2 minus transport. Because if you have a higher O2 minus transport rates, O2 is going to evolve into the gas phase, and then you're going to have these bad gas phase reactions that are taking place. And the matching can be done by by tuning the dimensions of the membrane, mainly the thickness, and tuning the surface area of the catalyst by designing this porous system on top of that membrane. And
can you please tell what specific rates do you have per square centimeter?
So in this particular case, the problem is that the design of this membrane, the fluid mechanics around this design is not really good. So you have lots of things that are moving past the membrane that are not encountering the catalyst. So they're not operating in a kinetic regime. So we have to go in a tubular membrane and that's what we are working on. And tubular membrane where we can convince ourselves that we are operating in a kinetic regime. So our rates under these conditions are relatively low. It's micromole per minute per centimeter square.
So, and limiting stage is just ion conductance.
For these systems that I have talked about, but I think we can design membranes that are thinner that allow us to conduct ions with high rates.
And but not electron conductance.
Yeah, I mean, for this LSGM,
the short circuit.
Yeah, you wouldn't. So for this LSGM, this is really not a good material as I show here. And here you have to enable electron conduction by creating extra pathways by putting, for example, nickel on some other metal. And that actually has also negative effects on catalysis because that can leach over time into the catalyst. And then if you have nickel encountering this reacting mixture and product, it's really going to make that B goes to C even worse. So you end up oxidizing more. In this case, that's not the problem because we don't have the nickel or whatever. So the way we can accelerate this O2 minus transport is to make the membrane thinner.
Yes, still you have always an option of short circuiting it outside.
Yes, you're talking about electrochemical pumping.
Well, thanks.
Yeah, you could do that too.
Okay, thank you very much. I would say we should stop the discussion now. If you have further questions, you can always find the speakers and send them an email, for example. But I think it was a very good session. Also, I want to thank both of the speakers for their very nice presentations. I virtually clap my hand again to both speakers. And also, I thank you, the audience, for staying up. So long for staying up for the let's say eastern part of the world, and for the western part I wish you have a good day in front of you. For me it's just the afternoon. I will get a coffee now and get back to work, and I hope to see you all again tomorrow. Yeah, coffee. See you tomorrow. Bye bye.
Thank you, Hans-Jörg.
Yeah, welcome. Thank you.
Thank you.